Yeah, we might need one more chair, it looks like. But they're all tied together. Full service here. We'll take you through this. So this discussion today is multifaceted. I'm here. I'm Neil Bund. I'm the CTO at Scalar Decisions. We operate Studio Cloud powered by Intel, and we're here to kind of discuss a couple of announcements associated with that service, describe its gestation and what it really looks like and how it impacts overall workflow and pipelining for our render clients, how that's expanding as a result of this announcement with Intel. We have a couple of panel speakers here. We'll do a Q&A session around some of the value adds and some of the trends and directions, right? Yeah, I think, for studios when it comes to obtaining sufficient compute, render capacity, and the performance implications of that. Maybe have a quick conversation about compliance and some of the nuances that everybody kind of struggles with. And we've got Jim Brinker here from Intel, the Senior Director for Worldwide Data Center Practice, to talk a little bit about the trends and directions that are driving Intel towards some of the innovations that we're announcing are part of Studio Cloud powered by Intel. So to kick it off, a little bit of history and background of what Studio Cloud really is. Studio Cloud is a service operated by Scalar Decisions, but it started actually out of a community need, right? As with all great innovations, most of the time things come to light when people identify a need. And in the Vancouver studio group, so the Vancouver area of Canada, they identified amongst several key participants of the studios back in the time, so this kind of the 2012 or so era, this desire and need for a more cost-effective, less capital-intensive method of obtaining large-scale compute, and quite frankly, an identification of in the early days of cloud here, of the ebbs and flows, the peaks and valleys of different people needing different compute at different times. Digital media is a relatively small world, and so people work on projects for defined periods of time, and somebody may be having a very strong up period while somebody else is a little bit more idle or needs less capacity because of where they are in their workflow or in their projects, and recognize the opportunity through a community-based design to actually set up an exchange. And Scalar Decisions, we're a systems integrator in Canada. We have about 350 people, about 190 or so of us are technical engineers, and then a supporting staff and sales staff to support that in Canada. We recognized and participated in this community and recognize that opportunity and put forth a proposal in the community to build that. We invested about $4 million in building a purpose-built data center designed for very intensive compute environments around power, cooling capability, and most importantly at the time around some networking capabilities. So the need for dark fiber, very low latency networks for quick extension of the local area studios. And what's happened over time is that service has expanded across Canada into a number of other locations. So now Vancouver, Toronto, and Montreal are the primary hub spots for that, with plans for expanding that beyond as the needs grow. But what's interesting is it started out of the concept of essentially a 3-year rental agreement where members, as part of Studio Cloud, would be able to exchange nodes with each other over time. So if, for instance, you had too much of a capital outlay and you had an idle period, you could recoup some of that through the purposes of an exchange. So kind of an early stage financial style market associated with render concepts. That's matured quite significantly over time. And what's interesting today, and the reason we're kind of having this session today with Intel, is that we're announcing a very strategic partnership with Intel. Studio Cloud is being rebranded Studio Cloud powered by Intel, and we are embracing each other both technologically, skills-wise from an engineering perspective, and financially to make even lower cost and more effective short-term burst rental and short-term acquisition of nodes with a much more active market behind it. And we're also announcing at Scalar a partnership with Conductor to enable hyperscale burst into public cloud, again using Intel technologies. So really starting to paint the picture of an end-to-end capability for our digital media clients whether they want to acquire their own equipment and host it themselves, whether they want to acquire that equipment and put it into a managed facility, whether they want to acquire that on a short-term or rental style basis in either kind of 3, 6, 12 or beyond type terms, or also embrace hyperscale burst. And so basically, regardless of where you fit, both in your pipeline and your workflow, you're now able to be serviced around these capabilities. And that's due to the partnership with Intel and some of their coming technologies. So as I said, this is a very strong two-sided investment between the two organizations. Probably will reshape the face of rendering and acquiring compute and eventually storage capacity as well, both across Canada and probably across North America and broader organizations, in the major centers around the world. The interesting element about this is it helps expand a service that had historically been predominantly predicated on kind of contract terms, a year at a time or whatever, and this allows us to become much more flexible in those contract terms where the simple sign up and acquisition of nodes can happen in 3 or 6 month chunks, but there is an active exchange. So anytime your nodes are not used, they're idled, they can be basically released or offered into a pool for other studios to kind of bid on and capture that excess capacity and use it very similar to kind of a spot type market in terms of that capacity, and also to recoup that capital investment. And so really what it means for a great many studios is that you're now able to invest more in more capacity, knowing that if you happen to have a lull or a break between contracts that's not actually going to encumber you financially, there is a method to recoup, because inevitably there will be somebody in that marketplace who's willing, or at a different cycle in their workflow and pipeline and their job schedules, that they can use that capacity and you can recoup that investment. And I think that's very significant for most organizations today. So how this all actually works, and this is a fairly crude sort of diagram, but, for every studio, one of the key elements to it right now is predominantly focused around dark fiber, very low latency connections to local studios. That's extended now also by another partnership with Console to provide cloud connectivity and dark fiber direct to cloud for the hyperscale burst elements. But clients engage through dark fiber directly into a facility that scales or operates and manages specifically for studio cloud type workloads, high intensity workloads, and are able to access highly advanced systems, the current generation of Broadwell, and soon to be, as we populate it, the Intel Skylake and Purley type systems for enabling advanced render on those elements. And at the same time, if they choose, can also engage with us around the support of Conductor to provide that overage and super peak burst capacity into public hyperscale, again with compatible facilities, often based on Intel Skylake architecture, such as Google's GCP Cloud, which has been one of the earlier adopters of Intel Skylake and is rapidly deploying it. And so from an adoption perspective, really what this means for clients is you often have a steady state workload that you need to service in terms of your capacity. It's what you plan for from either a capital or operating expense element. We can now match your expenditure and your desired expenditures for your business model. Whatever your CFO kind of says you need to be at in terms of your cost per node, your cost per frame, whatever that is, we can actually align to that in terms of acquiring the most recent technologies, and also servicing that through all the way from returning and exchanging nodes with your peers in the community, or through burst workloads and excess capacity, and ensure that those are available to users in a very well-defined, compliant, and quickly accessed manner. So what we've got, as I kind of indicated, we've got very short-term rental needs. We've got private client connections. We have internet access capable on all of the sites, and we basically have this deep ecosystem integration now between Intel Cloud nodes, Conductor, Console for connectivity, and dark fiber, which really means that any studio that wants to access this technology can do so quickly, efficiently, in a compliant and air-gapped manner if they want, and we will help assist with all the other compliancy needs for handling sophisticated workloads with MPAA, Disney, or Marvel type compliance elements associated with it. Today we have quite a large number of clients, so if you're not familiar with Studio Cloud or you've never seen it before, we have some of the top organizations in advanced special effects and render in the world already using our sites, many of which are actually up here on the panel, and we thank each of them for joining us, and we'll allow them to kind of talk a little bit about how they use this site and some of their perspectives on how the acquisition of render technologies has changed over time, and maybe some predictions for the future. This is a technical talk in theory, so a little bit about tuning and some of the nuances around the Intel architecture. So really, why are we announcing this, powered by Intel? Why make that decision? There's plenty of other architectures out there that people are dabbling with and playing around with. Not the only processor that's in town. We've spent a ton of time in our business. We spend time both with digital media and high performance computing, analyzing architectures and the benefits of those architectures. Intel's particularly interesting right now because they have a very concrete vision, and Jim's going to give us a little bit of the details around what that vision entails around the modification of technology over time to focus on application performance. And so these new generation systems, particularly in Skylake, are really interesting to us. They achieve incredible balance across the system, so big gains over traditional Broadwell, Haswell. I mean, I'm naming code names. You may or may not know them as that. But the traditional Intel and AMD architectures have passed. This Skylake architecture leaps well ahead in terms of capabilities in memory performance and overall system performance when we kind of compare clock speed, clocks, advanced acceleration technologies such as AVX and SIMD extensions, combined with the ability in the future to expand into a number of different acceleration components that are all on the Intel roadmap. And as applicable, those components will become part of the Studio Cloud environment as they're released by Intel over the next couple of years. And they have an incredibly strong ecosystem. So one of the talks right after this one and several other talks here at SIGGRAPH are around performance tuning and the hand coding and actual detailed tuning that's been done on many of the commercial and open source libraries for render, whether that's OSL or whether it's examples like RenderMan, where significant gains have been achieved by actually going in, identifying the hotspots in the pipeline code, and removing those hotspots and enabling dramatic speed-ups when you interact with this new technology. The other element that we're particularly interested in is when we look at the bottlenecks inside a pipeline, there's an increasing focus on the bottlenecks associated with storage caching, and the movement of storage data from one site and one location to another. So Intel's innovations in the future, both around their fabric technologies and around the Optane technology for storage acceleration and highly deterministic storage performance, so both read and write at a highly deterministic level, become particularly interesting to us, and those technologies are on our roadmap to kind of include into the Studio Cloud offerings as they become generally available from Intel. And so we're quite excited about those. They will have dramatic impacts on the overall efficiency and throughput that people see out of their compute nodes. I think the other element, and I think this is a really important element that everybody understands as we start to kind of talk about detailed processor specifics, is understanding some of the nuances of this new architecture. Historically, when I go out and talk to digital media and HPC clients, there isn't enough attention paid to the details of exactly how memory controllers work, what the memory balance is on a system, how to optimize for those, or how to identify codes that are properly tuned for some of the acceleration elements. And so when I talk to clients and they kind of say, well, I jumped from one generation to the next, I didn't see much of a speed up or this, that, and the other thing. When we stare at either how they configured their own systems or the applications that they use, they've failed to understand the nuances of both building a system with very tight balance across the entire system pipeline. So the memory to CPU, CPU to CPU, and the NUMA effects, and the elements that come into play in terms of network and actually making sure the workloads can get into those nodes. And then we also routinely run into the challenge now, and particularly with the Skylake systems, of people failing to kind of understand the subtle nuances between system levels, so such as the bronze or gold or platinum tier in Skylake. And even in the gold tier, there's kind of two tiers to gold tier if anybody sat and stared at scalable processors. And so kind of as a trusted advisor both to our clients and in the design of Studio Cloud, we've spent a lot of time analyzing exactly what those processor balance elements need to be in these systems, and it will help guide our clients and help guide all of you when you kind of contact us in proper selection of systems so that you can actually exploit in your pipeline all of this innovation that's kind of come into the hardware sphere. And the last part is obviously compatibility. You know, many of these projects are long-running projects. You have multi-generations of hardware often in your sites or using other partners that are doing workloads and providing things between studios, run on different systems. The other major element to the decision to kind of standardize on the Intel technology platform really is focused on that compatibility, deterministic software execution from one client to the next and between different engines is very, very strong in this space without changing and altering different processors, different rounding mechanisms, and those sorts of things that can creep into large scaling, large running jobs when you mix architectures. From a futures perspective, we're pleased to announce because of this partnership with Intel, we're going to be working on a number of different areas. One is enabling our clients to do wider level and larger scale type rendering. So this allows us to create much larger node types, much larger core count types. In fatter nodes, that means that we also have to solve some of the elements around networking. And so we're working on innovative early stage work with new fabric technologies that are available to increase that performance. As I mentioned before, we're working on the storage layer and caching. The implications today are already kind of flash and SSD, but when we look at Optane and the other 3D XPoint evolved technologies, there's a number of things that start to come into play all the way into kind of late next year when we start to look at some of the very interesting future technologies and roadmaps that Intel has for dramatically improving the performance of systems through the use of innovative Optane packaging. And then we're, as I kind of indicated before, through our partnerships with Console and Conductor, we're looking at the hybridization of systems. How do you actually move workloads much more efficiently from bare metal air gap type nodes into container type systems and into hyperscale burst and have that all perform as part of your pipeline in a seamless, easy to manage manner. And so those are the things that we're working on in Studio Cloud and are the results of this co-engineering partnership that we've got with Intel and the investment in people and engineering skills between the organizations. So I'm going to hand this over now to Jim Brinker to talk a little bit about Intel's perspectives on large-scale compute and really what's driving the innovation in their platform that we're putting to good use in Studio Cloud.
Great. We'll tag team in. So good. I'm just glad that Neil said, you know, why Intel? As long as there was a chart up there that said that, then we were in good shape, and it wasn't why not Intel or something to that effect as we went. But as mentioned, my name is Jim Brinker, and you know, by way of introduction, just real quickly, I run the worldwide sales and marketing for a new division of Intel, you know, that we're calling Scalable Data Center Solutions, and it's really driving a lot of our future engagement models. So if we fast forward, and hopefully this talk will make sense as we go through it, but as we fast forward to 2020, 2022, 2025, you'll see that there's a real convergence of technologies, market trends, things like that, and Intel's trying to prepare for that. But I've only been here about 18 months before coming to Intel, and this is where I enjoy coming back to SIGGRAPH. I was with Silicon Graphics, SGI, for a number of years, and I actually was there for running their media and entertainment business is when I first joined SGI, and we were going through the whole digital transition, and everything was taking place in that environment, so it was an exciting time. And prior to that, I was at Sony Corporation and running Sony Broadcast from that perspective. So we went from looking at, you know, HD coming into vogue to, you know, the whole digital transformation and 2K, 4K, et cetera. And now here we are today with some of what, you know, Neil was talking about. So it's really, you know, nice for me to come back to this. So what I'm going to talk about today, it's hopefully kind of a backdrop to the questions that will come out, but also what Neil was referring to, a lot of the market trends that are happening out there that's driving some of this digital change. In addition to that, there's technology trends that are taking place, and we'll address those of really some shifts in that and where they begin to converge, and then go through how Intel is going to, you know, is working to address those changes, and then bring it all the way back to the Intel Scalar partnership and what we're doing going forward. So as you look at it, and I think you can see this, the flood of data is out there and just getting bigger. So, whether it's, the autonomous cars, airplanes, smart factories, if we bring it into this world, you look at going from, HD to 2K to 4K to 6K, you're really dealing with just a ton of data. In addition to that, you look at it, it's different sets of workloads, and they're exploding. So these two things are both happening at the same time. So whether it's the Internet of Things, business analytics, AI, or exascale, which is, the big convergence of all this in the high-performance computing world, they're truly exploding, and you've got bottlenecks that are coming from that explosion. So these are some interesting facts, when you kind of fast forward and look at, where business as usual is not business as usual anymore. Over 2,000 CEOs are saying they're going to base their strategies around the digital transformation. So they're going to align their company to what's happening in the digital world. 40% of the top 20 will be disrupted, by 2018 and beyond, tied to the digital transformation, and the workforce is getting younger, which is good news for those coming up, and maybe tough news for those of us that have been in this workforce for quite a while, but it's clearly a lot of change. So when you look at what's happening within that world and what the bottlenecks are, you kind of can bucket it in a few different buckets. So one of them is clearly, the system bottlenecks. So whether that's I/O, storage, Neil referred to a lot of those areas, resiliency, or software optimization. You really see the bottlenecks coming there. The other is, infrastructure and this divergence of applications. So you've got, how do you handle analytics versus HPC or artificial intelligence or machine learning? How do you handle visualization? So all of this is kind of coming in from that. And then the cloud, and the cloud is out there, it's here to stay. But how do you deal with the cloud, the hybrid cloud, the convergence to the cloud, all of those environments, and work closely with it? And, in here you could have easily added security, particularly based on the news that popped out yesterday, but, clearly it's happening everywhere. And you see that as a major issue that you're dealing with in that. So just to give you more rosy pictures out there, this is just the beginning. So when you really look at this rate of change that's happening between now and say 2022, we were at a talk with BMW. They said autonomous cars will be mainstream in 2020, which isn't that far off. So you begin to look at it, the trial we're doing with BMW right now, it's got 3 locations. They're putting 100 cars on the road. Each car in that trial is taking 2.2 racks of data to process what's going on inside those cars. So you begin to see what's happening, and it kind of comes home to you with what you're dealing with, and it's going to happen across the boards. So then kind of getting to the good news and all this, what is Intel doing? And what we're really doing is moving away from just compute and trying to look at that overall solution of what's going on and the convergence of all this, memory, fabric, storage, software, and investing heavily in all these, and as they begin to integrate and come closer to it. We're also looking at code modernization and code optimization, because clearly going from the codes that are written today to the parallel processing codes of the future, you've got to change. And the more and more customers we talk to, they say they understand that. They're not afraid of that change, but how do they get from here to there? Right? They can't just shut down operations and bring them back up in 2022 and life is great. They've got to migrate these codes as they're going forward, whether it's GPUs or whether it's Intel processors, whatever it might be, that has to happen. So as I mentioned, if you look at this tighter component integration, and this is kind of a build on the last slide, you can see that you start to see the advantages in bandwidth, in latency, density, power, and you can bring your costs down in the overall thing. So again, as you're trying to get to that world that's out there, this is key to it. And probably the best example, and this is kind of a busy slide, but this was publicly announced a little over a year ago. And it's Intel going after the Argonne National Labs. It was called Coral, which is the pre-exascale program that was won by Intel, by the Department of Energy. It's being installed right now in Chicago, and we're driving to a future, type of architecture. If you look at where the real changes come, and Neil brought this up in his talk just a little bit earlier, you see the changes in, in-package memory bandwidth. You see the changes in some of the 3D crosspoint, which is a memory fabric combination that's really highly optimized towards that. And you're starting to move up that food chain. And what this is doing is driving close to a 700x performance gain over today's technology. So then you start to get at the problems that we talked about in the beginning of here, and you begin to get the compute power and the processing capable of doing all of that, and then also capable of driving out here with what we're trying to do with Scalar and Studio Cloud and that environment as you start to move forward. So all of this begins to come together. But it's not just about exascale. So, you look at exascale, it's clearly going to improve science and what's going on there, but, it can improve airplane and manufacturing design. There's something called the hypersonic design that's out there for 2026, 2027, which seems incredibly Star Wars and out there in the future, but it's very important, and you need this kind of compute power to be able to do that. In media and entertainment, as we talked before, you start to really move up the food chain and what you're able to do in rendering and what has to happen, and you need this power to be able to do it versus what was done before. And then there's healthcare, autonomous driving, a number of applications that might be out there. So the real goal, when you hear, the race with China and the DOE and exascale and all of these things, the goal is not exascale. Someone who mentioned it earlier said exascale is really just a point in time as you're going forward. Everybody's focused on it as a goal, but it's just a point in time. What's really important are the applications that can come out of that, which is where I think we're going to focus and and a lot of the focus needs to be. So finally, where Intel is going, and this is the last slide to set the stage, is that we've always traditionally been an ingredients company, and we were very good at it. But when you look at this integration, you look at some of the acquisitions that have taken place, whether in artificial intelligence or memory or some of the FPGA type of architectures and things, you've seen Intel acquire more and more in those areas. It was to build out a portfolio and really become much more of a solutions company. So that's what we're in the process of implementing. That's the group that I'm standing up to be kind of the leading edge with that. And what we're looking to do is really find avenues where we can differentiate, where we can add value from an Intel perspective, whether it's in things like some of the excess capacity that Neil just referred to in his talk, whether it's in areas like financing or creative business models or things like that. Those are all areas that we'll be focused on going forward. And I think that is it. So we can move from there out.
And so that was the mandatory, first half hour of this session. But I think, we're probably all more interested in kind of the panel discussion here. And so, over at the far end, we have Troy Brooks from DHX Studios. We have Jason Dodswell from Dark Horse 10. And we have Saker Clipston, hopefully I didn't brutalize your name too much, from Zoic Studios. All who happen to be Studio Cloud users, but I think even more interesting is, represent deep experience across the industry with pipelines, technologies, optimization, and really where digital media has come over the last kind of 15 or 20 years from kind of the earlier days and simplest forms of things to what is now a sophisticated environment of physics simulations and advanced rendering and different elements inside that pipeline, increased complexity, but also an increasingly challenged financial model for everybody, right? That balance between capital, operating costs, bidding on projects. Like There are a lot of people involved these days. And so your experience is probably very helpful for lots of different people. And I thought, maybe you could each take a moment and just describe your roles and your various studios, some of the successes you've had as a first stage, and then we could kind of pose a few questions here and talk about the changes in technology that you've seen kind of over the course of the last decade or so, how you kind of think things are going to change over the next little while, and where some of this discussion that, Scalar and Intel are having, the parts that you agree with or the parts that you disagree with, if you have some. Because as we indicated early on, Studio Cloud really was born out of community engagement, community involvement in solving those problems. So I think it's interesting to kind of have that discussion around those perspectives, if you don't mind. So Troy, you want to give a little bit of your background and perspective?
Sure. Is this on?
Nope, not on.
No.
Can you talk loud enough? Sean, can you hear Troy?
Sure. So, my name's Troy Brooks. I'm the VP Technology at DHX Media. For those of you who don't know, we make kids animated TV shows. We have about 1,000 people across Canada working in a couple of different studios.
Do we need the mics?
My Little Pony. No, thank you.
Oh, for the video.
Sure. Yeah.
Forget
So,
about that.
better? There we go. So yeah, I work in that capacity with DHX Studios now. In the past, I was actually head of studio at Digital Domain, one of the original sort of 3 customers that got Studio Cloud going in Vancouver, along with Jason. And full disclosure, I spent a couple years working with Scalar on building out Studio Cloud across Canada, helping expand it into Toronto and Montreal. And I do think it's been a very positive force in the industry, and particularly in the cities where it's taken root. The business has got increasingly strained by the need for tighter and tighter margins, whether it's on getting tax credits in tax credit advantaged locations like Canada, or just trying to sort of squeeze more efficiency out of the operation. I was struck actually during your talk, Jim, the notion that even as we try and refine our pipelines and refine our CapEx models and our OpEx models, there's increasing focus on the granularity of the design itself, the silver, the gold, the platinum things, the different, compiling for optimization for different workflows, and the focus on more efficiency on interchange between storage and compute. In the past, I think, mostly we budgeted for, frankly, the number of machines we could afford, and then you fit the show in around that kind of parameter. But increasingly, as we can go to this kind of burstable model and be a little more judicious in the spend, hopefully we get a better product and actually make a little money for a change.
Thank you.
Yeah,
Jason?
Unique concept.
I'm Jason Dalzell. I'm the founder and CEO and creative supervisor of Dark Horse 10 Pictures. We're a film production company in Vancouver, but our strength and expertise is in visual effects, and that's where most of our talent comes from, about 20, 25 years of experience. Jim, you mentioned a couple of names just from my background. SGI, you were part of SGI when I was an artist 25 years ago here in Los Angeles. Talk about barrier to entry. It was companies only like Sony or Disney or Lucasfilm that could afford to pay for the SGI systems. And when I was an artist, and when Troy was also writing code on a lot of these boxes, the box, the hardware, the software at that time, 1993, was $250,000. That same technology today is less than 10,000.
We used to refer to that as the good old days.
But I think that's fascinating, right? Because that ties right to the commoditization of this sort of workflow, and it also means that there's incredible things people can do, even with desktop systems that we can all afford today.
Absolutely, and I think that's been a trend, and we talk about this. I mean, we're media and entertainment. Our main clients right now is Hollywood. Hollywood, although appears to be in the business of making films, they're in the business of making money. So anytime there's success, they want it repeated, and they want it done cheaper, better, faster. How do you do that? You do that by putting the vendors, squeezing it down, going to rebate territories like Vancouver, New Zealand, London. And that's kind of where we come in. I've been part of building companies up in Vancouver over the years. That's where we did meet Scalar. You had a date of 2012. By which
I think it was even earlier than that. Yeah.
Well, earlier than that, the whole idea was abandoned. the studio group, Vancouver Studio Group was a conglomerate of maybe 13 companies, all ailing the same pain points. And about 3 years worth of work went through, and then we just left the idea on the table that no one would figure this out. And then Scala came along and said, well, we'll do it, we'll start. And we had the three founders, Digital Domain, Rainmaker, and Image Engine. With great success. That first year, there were 11 transactions, meaning 11 times that one of the three traded our resources back and forth. And I don't know how many members you have now, but it just kind of is this beginning of a great success story. Aldwin, who's a business partner with myself now, our CTO, when we started Dark Horse, we weren't inheriting anything from another company. It was a white slate, and there was no decision to be made. Scalar, the solution, even with Intel now, that's great news, is clearly the right direction, because we don't have the brain trust, the capacity to think ahead all the time. We're busy on the day-to-day, but if we have a partnership with Scalar, they're thinking ahead. They're thinking where we need to be in 2012, 2020, 2025, or beyond that. My other thought, too, in terms of, you talked about the new architecture, even with our clients, we can get a show come in, we know how many people we need to hire, we know how many machines and render nodes we might need, but the thing that changes is that we can't manage the clients, and the clients are now at a place where they don't know what they want, and they want to keep a show active till the very bitter end. And we're almost at the point, it's not quantum computing, but when we're working on an assignment, call it a shot, and the client says, I want it like this, and you get vague responses, our turnaround is we iterate not just one idea, we iterate the spectrum. Do you want this or that? And you give it to them completely, and they pick something, and then you move on. But we can do that because we have a burstable system. We get to the finish line a lot faster at a cheaper cost.
Very cool.
Yeah.
And Saker, I think we did Jim, so I'm skipping you. And Saker.
My name is Saker Klipson. I'm the CTO at Zoic Studios. We have 3 facilities, Vancouver, New York, and Los Angeles. We started up LA first in 2002, and Vancouver in 2010, and recently, almost 2 years ago, New York. We're about 400 people. We primarily do visual effects for episodic television. That's kind of what we're known for. But we do feature films and commercials, interactive projects. We recently started a new division called Zoic Labs, and we deal with big data visualization, sort of a VR component, visualizing that. So we deal with a lot of data. But as it pertains to Studio Cloud, we kind of got to ride on the coattails of you guys. They built an awesome facility. We started up a Vancouver office in 2010, and we needed a place to put all of our equipment. We were pretty small at the time. I think we're about 15, 20 folks, and within a year we had ballooned up to about almost 200 people, and now we're somewhere around 320 in that office. And the buildings in Vancouver aren't that great. They lack a lot of power, cooling, all that fun stuff. So we had built a small little server room there to host what we thought would be enough. But of course, everything ballooned up, and we ran into Studio Cloud and Garth and ran some fiber to Studio Cloud, and now we have about 8 racks of equipment there, mostly workstations, and we get to take advantage of burst computing when folks have render nodes available. So again, like I think you talked a little bit about it, we're very seasonal, probably around end of September till March. We tend to get into a crazy mode where we're almost in this like pilot mode phase. We're taking on more than our traditional workload, which is about 22 episodic television shows that we work on at a time. Once Upon a Time, you name it, we work on it. Game of Thrones, that sort of thing. I'm trying to recall names, but I only know them by 3-digit codes. It was easy when there was only a few. Buffy the Vampire Angel, all that stuff we started doing. But anyways, yeah, that's the crazy point. That's when we call up Chris, and I'm like, hey, I need render nodes, and sometimes he has them, sometimes he doesn't. But so that's why it's really great to hear this new partnership that hopefully we'll now have them all the time. We've dabbled a lot with cloud. I'll talk a little bit about cloud. I don't know if you guys have dabbled in cloud computing a lot or what have you, but basically in this last go-around, I call it pilot season, basically January through March, things start to get really hectic around Zoic. We take on probably another 10 shows on top of the 22 regular shows. And these shows are very, very intense. We're working with a range of different clients. And like you said, we have to iterate really, really rapidly, really fast. And we peaked up to around 5,000 instances, which was around 160,000 cores in 1 month's time with Google. It was a fight to get that many instances. Everybody thinks cloud is very easy. Hopefully, Conductor or
Conductor, yeah.
Conductor will help ease that situation. But cloud is very difficult if you don't have a big pipeline team and you just want to, throw render up there, so throw 1,000 frame render up there and expect to get it back in an hour. It's not that easy. There's a lot of infrastructure on the back end that you need to deal with, and a lot of configuration, as well as the pipe to the cloud, making sure you have ample bandwidth. That's we have a 10 gig connection. We're expanding to a 40 gig connection to Google, and maybe beyond. But when you throw up a sequence of 1,000 frames and getting it back at the same time, that gobbles up the pipe pretty fast, and everything else ricochets down. But I'm babbling here. But it was an interesting experience for us. In a short period of time, we had to scale up to 5,000 machines. We could have taken on another 10,000, I would think, at least. And mostly we deal with V-Ray rendering at Zoic, but we're doing a lot of terrain data, so using Terrigen, and we got to take advantage of some of their newer processors up in the 64 core area, which was pretty exciting to see the type of power we can get out of that. And it's interesting to see the balance between on-prem and cloud. We've always built everything ourselves. We've never really reached out to an integrator except for Scalar to help with our colo. So we've built, Johnny over here, and I have built numerous data centers in Los Angeles, New York, and even Vancouver. And it's a tough proposition. We have so many things to deal with these days, which is why we kind of lean on Scalar now to help augment that. Optimizing applications, making sure they can work in parallel are things that we need to focus on, and not dealing with, is my server going to be properly cooled?
What about compliance, privacy, and security, right? This comes up a lot in our conversations. Studio Cloud kind of has a variable model. We can go everywhere from air gap type systems when you kind of want that level of assurance, up to all sorts of different integration points. I'd be curious, in Jason, Troy, your experience as it compares, to the experience with hyperscale. Both how does hyperscale kind of fit in that, and kind of picking where to do and run your pipelines, and how does security factor into some of those decisions as well?
It's interesting. When I was at Digital Domain, of course, we had to deal with MPA and Marvel level security, which is pretty stringent. Now that I work in television, the constraints are much less, but the model stays the same. I mean, you still have to maintain control over your data. Rendering in the cloud, although we haven't gotten to it ourselves, I don't think it's Google that really sort of presents the concern there. The thing that I think is interesting because Google's pretty secure, they kind of got that knocked down. But I think the thing that's interesting is that as the security model evolves, and frankly, as the clients become more comfortable with it. I mean, the initial constraint, from Marvel and most of the big studios on visual effects movies was, no, you just can't, we're not going to let you, it scares me, I don't want to think about it, let's talk about something else. And as time goes on, and we've been able to present, models, financial models that show that it makes sense, they've relaxed, and we've gotten into the security issues. The thing that I think is interesting is the more granular business opportunities that it prevents. When we started Studio Cloud with Scalar, we had to have air-gapped networks. And so you couldn't share, a half rack or less than a half rack on a single switch. All of the networks had to be entirely air-gapped. And you couldn't have, the repercussions of that were that you couldn't really afford to do this for less than 30 days because you had to physically patch things, and the cost of having someone in the data center moving things around and sharing resources that way was prohibitive. As the security models evolve, you should be able to get to the point where you can have very granular, metered, both licenses and machines, and share them within a switch for much shorter periods of time. And I think that'll just make it that much easier, even within a private cloud, or, Google, obviously that's not a problem, but in the private cloud, being able to have that kind of granular performance makes it even easier to take advantage of resources like that.
Well, I think that's fascinating because you actually touched on something that comes up a lot, and that is, needing to manage licenses, license management, and, we're making huge strides on kind of the hardware level and the capabilities, whether it be hypervisors or containers and the shareability of hardware infrastructure, but sometimes there's actually a lag in the commercial terms associated with some of the software you're using. Jason, I'd be interested, do you run into those challenges? Are you are you spending a lot of time managing licenses both in a Studio Cloud model and in a hyperscale burst model, any of those sorts of things? And what do you think needs to kind of adjust or be changed there over time? How are you seeing the industry adapt?
Actually, I just have one point to that. I was on a panel much like this in the early 2000s, and it was talking about virtual render farms. They didn't even talk about the cloud back then. And the point then was, the single biggest impediment is the business models of the big software publishers, right. Autodesk and the rest. And they absolutely explicitly did not allow this kind of thing. They had provisions in the end user license agreement that said you can't use this license more than 3 miles from the physical address that we note on the contract. Obviously, that's all changed, but that was the key to really this whole thing coming around. Some people were doing it on the DL for a number of years before that, and that's usually where these kinds of technologies get started. But yeah, that's in my experience, that's been a huge part of this thing being able to expand.
Well, I don't know that it's entirely been solved. I'll be interested in, Jason, your perspective on it. I know we've done a lot of work at Studio Cloud, enabling even things like Maya I/O and the proper metering of those sorts of services. Clearly it's topical. Clearly there's some interest from the software vendors in kind of enabling it more and more, but it's still much earlier days. So the level of sophistication of the level of sharing we can do at a hardware and at a security level still seems to kind of be well ahead of that level of sophistication in terms of metering. I spent some time at IBM, we used to meter software by MIPS in the mainframe days sort of thing. So it's not that it's never been done before, it's just still early days. So Jason, what are your perspectives on those?
Yeah, just back on the licensing, that when we got into the Scalar render farm solution, that was one of the first issues, which is that we could rent someone else's render nodes and image on them, but then we still had to go out and buy the software, which equally would be our hard-earned cash, and it would sit idle after the work was done. And I do believe it was actually Paul Kerr, CEO of Scalar, that actually reached out to Autodesk as an example and said, hey, why can we just erase these international borders? And actually Scalar kind of made it happen. So every other vendor, whether big or small, is now following suit. We see that even with some of the new emerging technologies we use. We use a new renderer called Clarice, or I'm thinking of the Yeti software. When we need to burst, they come to the table and say, well, just here you go. You can have them for 20 days. So they just kind of match our demands on that side of it. And kind of touching back on the security, it's paramount, I think, with all of our clients that they want to know that we're safe and secure, and I think that Scalar does a lot to the infrastructure to protect all that data. I think the next evolution is going to be managing the security of what shows up on the monitors. While we still chase down a need to be faster, better, cheaper, we have to seek out artists all over the world, and we can't necessarily contain where they work or reside, and sometimes they're in Tibet. So how do you push out to where they are and control the monitor situation and ensure that the images up there are contained and protected? So I think that's the next layer of security we need to look at.
Yeah, that's a fascinating challenge, and you're not the only ones that kind of deal with that. From a Scalar perspective, we deal with that not only in the digital media space, but we're actually dealing with that in kind of a more commercial enterprise space with organizations like police forces and hospitals. The same sort of thing is, it's not necessarily the file disappearing, sharing, it's somebody taking a screenshot of the file these days, or taking a look at things and reading scripts and all these other different things, which is an intractable problem that there aren't a ton of great solutions to yet. Switching gears ever so slightly, there was the comment earlier on about, the challenge of networking, right? Network bandwidth, moving data back and forth. One of the elements that we've kind of tried to focus on from a Studio Cloud perspective was where at all possible, and we're continuing to expand the locations where, Studio Cloud is geographically located, but we often do connectivity through dark fiber and anything we possibly can to keep latency down and bandwidth up. How much of a constraint do you think that networking is for things such as, the virtual desktop solutions for artist and render, or even just the data movement associated with burst? Does the latency play more of a problem, or is it more the bandwidth challenge that you have?
Not my area of expertise, but I think that the latency, where you have global companies that are in different territories and you want to share work, you have a latency issue. I think we've seen companies like Sony ImageWorks relocated their whole data center from Los Angeles to Washington so that their workforce in Vancouver, which is 1,000 people, could be on the same PCIP systems at that data center, combating latency issues there. So it's an ongoing matter, I think. Bandwidth, again, more needs to be done in less time all the time, so bandwidth continues just to be a factor. And I think as everything improves, then the demand asks for more improvement, which is that chase we're always in.
Right. Yeah, as we move into kind of 4K and stereoscopic and all these other elements that we can do, and we can build systems kind of using Intel technology with a really high bandwidth inside a data center, one of the challenges Scalar's constantly looking at is more and more that link to the outside world. It starts to, if you've got 100 gig throughout your network, even your 1 gig or 10 gig pipe into the data center starts to feel like those old modems clicking at when we move to DSL lines. You can hear the carrier signal, you want to tap the frames out even faster. So we're always looking for innovation there.
Right. I think the one thing that wasn't mentioned, when you look at latency, bandwidth, security, all of these things, they add cost to the model. And how do you solve all this, either in network or in processor or in a way that can reduce the cost of the overall solution, particularly when you're shipping it around the world and doing things like that. So that's a key area to try and look at when you're looking at the efficient models.
Yeah, thanks. Now, we only have a couple of minutes left, and we have a few participants in the audience. I guess the question was, are there any? Oh, did you want to add a comment? Sorry.
Oh,
skipping you over there.
No, not at all. I can go ahead.
How do you field the first question?
Oh, okay, sure, you can field the first question. So I was just wondering, are there any questions? We've got a great panel of people, combined, we'll do that combined capability in the field. It seems like you're pushing 100 years, but, lots of different capability across each of you, and the experience of starting studios, dealing with these capital challenges, dealing with bidding on projects, understanding them, scaling your artistry, scaling your capabilities. Are there any questions that anybody has for the panel? Or about Studio Cloud kind of before we wrap up the session? And this is where everybody gets really quiet. Nobody wants to ask questions, but fire away.
So I guess this is for any of the people that have made these decisions for companies. Obviously, most of us don't start brand new with this is going to be 100% our render solution. How have you kind of moved to the direction of Scalar, integrating this with stuff you already own? And just like, I guess, legacy type equipment, and what advantages are you seeing with your ability to render here versus like on a piece of equipment that is in your rack room?
It's a very good question. We have all sorts of equipment in Age, I should say, on-prem, physically in our building, physically at Scalar, and now Google Cloud as well, right? And dealing with all that legacy equipment is really difficult. Artists are kind of afraid of the cloud a little bit. They have this notion that costs can get out of control, or it's not going to render the same as stuff that's on premise. We've tried to obfuscate all of that to them, so nobody really has to worry about that. Our pipeline team has spent a lot of time benchmarking our on-prem. So when we approach the cloud initially, and even Scalar, we look at the cost. What does it cost for Zoic to buy its own hardware, put it in like down to the square foot and the electricity and everything. We benchmark, we calculate all of that. In our render queue that we developed, we have columns in there that you can estimate the cost of what it'll cost to be rendered on a machine in Scalar's Colo and then rendered on a node or an instance in Google's cloud versus on our on-prem. And so our producers can begin to gauge, what are those costs and begin to project over the length of the project where my costs are going to be. Do I need to keep my stuff on-prem? And then, of course, there's fighting that goes on because everybody wants to go wherever the cheapest cost is going to be. And those numbers are always fluctuating constantly depending upon, are we bringing in the latest Intel processors with the newest memory, or are we taking advantage of a machine that we've had that we've depreciated already for like 5 or 6 years? And it's good enough for Nuke and it'll get stuff done, but it's not great for my, my 32 core V-Ray renders, that sort of thing, so.
Well, and we have terrible news for you because of this partnership and this announcement. All of those cost models
Hopefully all that stuff
go right out the window. We're going to have to rerun all those benchmarks for you.
Yeah.
All right.
He's got one more question too.
I just wanted to add something else there for you, John. I think that, our CFO, Greg, he found the sweet spot in financial documents that there's a value to own some of the gear and the rack, even in a colo, and then a mix of then having stuff that you rent and you do for bursting. Part of that is because you can still, as a business model, have an opportunity to amortize costs over your headcount over time, which is a good business. But Aldwin, you and I, we bought some gear, we moved it into the colo, and everything beyond that is a renting model. We've seen the variations, and I think the other part is we like to have the flattest render farm, meaning that you're not going to stick a job and that one stupid slow proc is going to sink the whole thing. So it's this gradual migration, moving things to secondary services, whether it's even storage that becomes nearline or offline or anything like that. You just kind of slowly move the old stuff out and away. But I'd rather promote the idea of just pulling a Band-Aid off fast.
And achieving deterministic performance is really tough. I think there was another question.
But just to add real quickly, this is not just a media and entertainment issue. We're seeing the exact same issue in oil and gas, in financial services, where people are looking at that migration to the cloud, but they're looking for kind of the interim step where one size doesn't fit all, and whether it's dark pools or flex capacity, or which is really what Studio Cloud is all about. We're seeing that trend across the board.
There was another question?
So it's kind of, how do you deal with, you alluded to the fact that sometimes you don't have enough capacity, you don't have enough machines on a cloud, so how do you deal with availability? So you need to finish by whatever, Monday night, and there's nothing.
So I think there's a couple of things that I'll give a bit of a scalar perspective, and that is the intention of Studio Cloud kind of fitting into that of there will be things that you already have as assets, probably your own capital assets, whether they're in my DC or your own really doesn't matter. The rental nodes provide some degree of granularity. So if you see that spike coming in the exchange, you can both offer and bid out for excess capacity, and every one of these guys can stare at the offer that you're prepared to make to acquire capacity maybe for a month or maybe a few weeks and say, you know what, I could actually give up some capacity to kind of take that money off the table. And so it actually becomes a much more of a financial exchange sort of model. Then you have obviously the capacity that we have from a pure rental perspective. And then finally, I think if you're running into those really last minute elements, you do have to engage and hope that you're able to do things through hyperscale bursts. But, as we've kind of discussed, the challenge with that is you have to plan for that up front. Like, it is not a simple process. You have to have redefined your pipeline. You have to have some of those partnerships, whether it's Conductor or whether it's your plugins, for Maya or whatever, to be able to go out and extend that. And you typically often have to have pre-configured some of those environments, whether it's AWS or GCP or whether or not you're going to try Azure, don't try SoftLayer, all those sorts of things, for those sorts of environments. And that's where, someone like Scalar can kind of come in and help you on those environments. And as part of our partnerships, across the service provider continuum, not only is there the partnership with Intel around Intel technology, but the great news is Intel technology is available at our other partners like Azure Azure, AWS, and GCP. And so as long as we know in advance that you're going to run into those sorts of models in your business plan, we can try to solve that for you in advance. But the last minute thing, I think it's a hope and a prayer and calling a bunch of friends and seeing what we'll all do for you at midnight, right?
Yeah. For us, it was really difficult at first, but because we have so much throughput that we're doing, so many shows that we're doing, they all have various deadlines. And so if you want to know like what happens when I have a delivery on Monday, well, many of those shows they sacrifice missing either smaller deliveries, we have to basically prioritize everything. And basically, like if we're doing Once Upon a Time and oh my God, this giant sim has to get out for airing on Monday, well, we can't not deliver. Like fans will be upset and we'll probably get sued, right? So, because they'll lose out on all the advertising money. So we basically throw the entire compute cluster, whether it be on-prem, in the cloud, or at Studio Cloud.
Installed Deadline real fast on your desktop.
I could talk about render queues a whole nother time. We use Rush and we're now writing our own, but that's a whole nother thing. Render queues for exascale cloud computing. It's a whole nother can of worms. That Deadline, I don't know. I'd like to see it do 5,000 or more.
Well, thanks, guys. I got the signal. We're a little bit over time. I really appreciate all of your input on the panel, and thank you for the participation from the crowd, and thank you for coming to the event today and learning a little bit about Studio Cloud. There's lots of us here. We're over at the Intel booth if you want to talk any more about these services, what it means, or any of these new technologies that Intel is presenting. And stick around because I think there's some secrets of optimizing RenderMan for Skylake and other Intel technologies coming up shortly in the next couple of sessions. So thank you very much, everybody.
right, good afternoon. We're really happy to be here. My name is Mauricio Cuervo. I am with Intel. I manage a strategic relationship. I work with Pixar. They are a pleasure to work with. They take advantage of our processors to the limit. They produce great products. They have really smart people, and they are a pleasure to work with. So it's my pleasure to introduce Alan Poor. He's the VP of RenderMan. He'll tell us a little bit about RenderMan and a bit of a historical context and the collaboration with Intel. Then we have Andrew Kensler, who has been working on the denoiser and how we collaborated on improving the performance of the denoiser. And there's Louis Feng, software engineer from Intel, who also collaborated closely with the entire RenderMan team on taking RenderMan to the next level, and we'll do a deep dive on the denoiser. We also have Alex Wells, who was a key contributor to the project. All right, let's get started.
Hello, I'm going to give you guys a quick little 2-second tour of the RenderMan history, which is quite long, as many of you know, but just to kind of set the context. RenderMan has kind of been in use for almost 30 years now. That comes with its own set of problems and challenges, but every one of Pixar movies has really kind of pushed the render in new ways over the past 30 years. It's kind of continually evolving to meet the needs of all of this stuff and all the new effects and realism that is coming on the market today. And in 2015 is when we kind of introduced our whole new architecture, the RIS architecture. That's the full path tracer that is fully modularized and basically will allow people to write their own integrators and BXDFs and flexibility in the pipeline that they can basically add the things that they need for the individual pipelines that are around. And so RenderMan has obviously been in a few movies over the past 30 years. Over 400, I think, the last count that we had feature films used in. And this has also pushed our software tremendously over the years in ways that you would never imagine it would be. And just a little marketing slogan here, we've been used kind of in 90% of all the Visual Effects Academy Awards nominees use RenderMan, and 19 out of the past 21 Oscars for visual effects have used RenderMan as well. And so with that, we can get a little bit into the trends over the last 30 years in this industry. And there's a lot of them, and I'm only going to talk about one. And I think it's the most common and persistent one that there is, and it's complexity. There's always more complexity. The artistic gains will always eat up all of the performance enhancements we usually meet, and we're continually challenged with each new set of movies to address these and get performance that's acceptable and can get rendered in time. You know, the realism is increasing, obviously. The number of objects, the effects, all these kinds of things are getting much more complex over time. Like, for example, here is a shot from MPC, The Jungle Book, and you know, this movie had over 1,200 shots in it, with 60 different environments, 1,700 assets, over 200 animals, I believe, hair, fur, water effects, all these kinds of things. And you know, you ask yourself how much of this stuff is CG in these movies these days, and it's obviously, oops, a little too far, almost obviously all of it. There's a lot of shots even in The Jungle Book that did not have any live action in them at all. Another example of this is Piper that went out in front of Finding Dory, and each of the sand pieces were actual geometry, procedurally generated. So this is kind of the scale that we're dealing with. They did that to get the look they needed with the light transport through the objects, as well as to interact with the individual grains of sand to get the characters interacting in the way and the artistic look they wanted. There's a Cars shot, Cars 3 that came out, and this is one shot that had over 6,000 lights in it. And you know, the big deal here is how do you sample these lights effectively? And there's a lot of people, smart people, working on how to do that. And we got that done and actually rendered after spending a lot of time optimizing how we sample those lights. But then I sent out a big congratulations to the team, like, hey, we did this, you got the 6,000 light scene rendering in a reasonable amount of time, and within 2 minutes, an engineer sent me a shot from the next movie. And this is Coco, and kind of the scale of this show is unbelievable. There is a point cloud light with over 3 million point sphere lights in each of these things, and over 100,000 other light sources in the scene and tens of millions of objects. So this is the level we get continually pushed for, and how do we optimize around this stuff? We created hierarchical clustering on our light selection algorithms to basically deal with this scale and these number of stuff that's going on here. The scientific visualization is another industry that pushes it. It's not just the visual effects industry. NASA is one of our customers, and their data sets are ginormous for the simulations that they use. And RenderMan is one of the few renderers out there that cannot handle the size of this, their data sets and what they need to get done. And this is only possible kind of with the marrying of the software and the hardware. You can't just optimize one and not get the other. And that's where we've spent a lot of time with Intel, which I'll get into in a second. But on the software side, we have all this complexity on the back end, but we don't want to expose that to the user and how that's all done. And we've been spent a lot of time over the past couple of years working on really 3 themes to help that angle of it. And they're about simplicity, stability, and speed. And it's pretty simple, and those are the areas that we've been focused on. Obviously, it's not how fast, necessarily your frame can render, it's how fast your artist can make a decision, whether it's the right look or your director can. And it's not time to first bucket or time to first pixel. We use this term time to first decision. That's really important, and that's what really matters at the end of the day. And so everything comes down to performance at the end of the day, as we've mentioned before. And there's kind of 3, dimensions that we measure this performance on in the group. One is how fast we can move as an engineering team. Having a code base that is, over 20 years old in some places. We've done a lot of cleanup in that over the years to actually make us move a lot faster. 2, how fast we can make actual render times, which is what most people talk about and how they refer to it. And 3, how, increasing artist productivity and how fast they can get stuff done. It doesn't matter how fast you make the software. If it's too hard to use or too cumbersome or not stable, obviously these things will take a lot longer. And so this brings in the collaboration with Intel, and we've been talking with them for about 18 months. They've embedded 3 engineers with the team. They've been very generous with their resources, very generous with their hardware, which we've appreciated a lot. They've trained us up on a lot of better ways to use VTune, profiling tools, about how to set compiler settings to get the most out of our renderer. They've actually embedded these 3 engineers with us. They're kind of working virtually, but it's been like they've been part of the team. They've helped us with kind of our light selection and optimizing that. They've helped look at our volume code and made sure we're doing anything that could be done there. But the 2 big pieces, and that Andrew is going to talk about here in a second, is the denoiser, which came from the Walt Disney Animation Studios and the Zurich research team. And we worked close collaboration with them to kind of get that thing up and running as fast as possible, as well as kind of the OSL piece of this, which is the open shading language. And those pieces, there's going to be a talk right after this by Max Leoni and other Intel engineers to kind of go over what that was done there. And with that, I'll turn it over to Andrew, who will talk about the details of what you're probably most interested in anyway.
Thank you, Alan. So I just want to acknowledge that this has been a collaborative effort across not just our group, but also with Disney Research and with Walt Disney Animation Studios. I'm going to talk about the denoiser here, but really some of the first research on this was done by Fabrice Roussel, who's now with Disney Research, and the initial code base here that we have based all this work on was done by David Adler at Walt Disney Animation Studios. So here is sort of a ground truth image that I'm going to show, and I'll be using this throughout the talk a little bit. It's admittedly programmer art, but it does serve to show the denoiser in action here. And in fact, relatively simple images like this, where they're somewhat uncluttered, can be more difficult to denoise since they tend to show the denoising artifacts more clearly. There's not really much texture here for noise to hide in. So here's that same image rendered at only 32 samples per pixel, and I've got some parts of that sort of blown up there. On the right-hand side is a difference between this image and that previous image. That previous image was rendered at more than 8,000 samples per pixel. This is only 32. We can render that image incrementally, adding samples each time and refining the image as we go. So already at this point, with only 32 samples per pixel, you can see pretty clearly how the image is going to look, but there's still a lot of noise. We can continue to add samples to that. Here it is with 64 samples per pixel, 96, 128, and then 160. If we flip back and forth and compare between the 128 sample per pixel and the 160 sample per pixel images, the difference between the two of them is much less than going between the 64 and the 32 sample per pixel images. So, with Monte Carlo rendering, as we add samples, there are diminishing returns on the amount of the reduction in the noise. However, it still takes the same amount of time to add those samples and the same energy cost on your render farm. We can plot the sort of the noise in the image versus the ground truth. Here, this is a mean squared error difference between the images at a certain number of samples per pixel and that 8K sample per pixel ground truth. And you can see that there's really an inflection point where after that, you can keep adding samples to it, but the amount of noise does not diminish significantly. Usually this particular plot is shown on a log-log axis, in which case this looks like a straight line. But the thing is that the times for render are not perceived as a logarithmic thing. So it would be nice if they were. So we'd like to be able to stop at that inflection point and then be able to do an image processing step to clean up the residual noise. And so here is the render at 128 samples per pixel, and on the right, it shows it denoised. So this combination here is much faster than simply adding more samples to it. And it gets us the rest of the way towards having a clean image. It won't be exactly the same as the ground truth render, but it's good enough for the eye. So I'll talk a bit about some basic denoising methods here. So to start with, you can do a simple Gaussian blur, where you use a weighted average of the pixels around each neighbor with a filter kernel that falls off spatially. So in this case, using a Gaussian kernel. If I do that, here's an image showing the 128 sample per pixel image with the Gaussian. It's not an image that you would use in practice, but it does show that a Gaussian filter is actually effective at removing the noise. But I'll also note that I'm showing this with intentionally exaggerated settings, just to highlight the effects here. In practice, you would use much more carefully tuned settings, and the effect would be much more subtle. We can extend this to take into account not just the spatial differences for the weighted blend, but also color differences. There's also a variant of this called the cross bilateral or the joint bilateral filter. And in this variant, the filter produces the weighted average of the pixels in one image, but uses the color differences of the pixels in a different image. So we'll come back to this idea in a few minutes. So here's the picture showing the same image, but now filtered with the bilateral filter. And you can see that for the point where the kernel that I'm showing is, roughly at that point on the dodecahedron, that it's blending the pixels on the one side of the edge with that pixel, but not on the other side. So the bilateral filter is edge preserving. It can blur fairly strongly in flat areas of the image, while mostly leaving the edges alone. Depending on spatial and color parameters, it can still underblur in some areas and overblur in others. So instead of directly comparing the color of a pixel itself with a neighbor, we can look at a small patch of pixels around each of those pixels, say a 7x7 patch around that pixel and its neighbor, and compare the corresponding pixels within those two patches. This is the non-local means, or NLM filter. And by comparing the patches of the pixels, it tries to identify regions with similar edge and texture shapes, and then blend those together. Note that in the classical non-local means filter, we consider pixels across the entire image as potential neighbors, and we don't weight based on the spatial differences. So here's an image showing what that looks like now. With the same pixel along that edge, you can now see that the kernel has chosen to blend in pixels along that entire edge, as well as some similar looking edges nearby, a bit of a ways across the image. So it's not constrained spatially in this case. In practice, most practical implementations of the non-local means filter do limit the neighborhood size that they'll search around the pixel for similar patches. But this usually doesn't affect the result too much, but it does make the filter more practical and a little less expensive to filter. Now I'll talk a little bit about the robust denoising, which kind of extends the NLM filtering even further. And this is the Fabrice research. This includes a few different ideas. Includes feature vectors, variance estimates, and multiple filter scales. So one thing we can do with the feature vectors, unlike photos, with a render, we have more than just the final colors. The renderer can output additional channels containing other quantities or features. And like the joint bilateral filter, we can compare the values in these other outputs to decide how similar two pixels are. It may be that two nearby pixels happen to have similar colors in terms of the color buffer, but a discontinuity in depth, for example, that tells us that these are from different objects and that they should not be blended together. This can greatly help to avoid overblurring. We can also use variance estimates where we estimate the amount of variance within each pixel. This is another quantity that the renderer can produce for us. And this gives an idea to the denoiser of how reliable those different features are. Where there's known to be less variance for the value in the channel for a given pixel, it can be more discriminating about differences when comparing it against corresponding values in other pixels. We can also apply the filter at different scales here. So one idea is to use a filter bank of filters applied at those different scales. We can use the different neighborhood sizes or different non-local means patch sizes and so forth. So the smaller filters will preserve more detail, but they'll also preserve more noise, and vice versa. Larger filters will remove more noise, but also more of the signal. So some of these will be more appropriate for some areas of the image than others. So having the variance estimates comes in handy here. Roussel uses the Stein's unbiased risk estimator, or SURE, to decide for each pixel what is the largest filter in the filter bank that it can safely use. And where there is less variance and the image is smoother, it can try to use the larger scale filter to eliminate more noise. Near edges and small details, it will use the smaller scale filters. That doesn't eliminate as much noise, but it does avoid damaging the detail. So here, the selection map on the left shows the which of the 4 previous ones for this particular image had been chosen, and the right shows the blended result. So there are some additional refinements that can be made beyond that and are used in the denoiser. One is to split by light transport. So we can split out the render into diffuse and specular parts. We can even go further than this and have things like caustic or other paths. RenderMan offers arbitrarily fine control over the split for the different light transports through the use of light path expressions. Those are effectively regular expressions that match against a string describing the path. But at a minimum, we'll split between the diffuse and the specular here. Generally, the more finely split we do, the better. And then each of these is denoised separately and then combined. So another thing that's very helpful is to take the render and divide out the texture albedo. And this gives us an illumination image. The illumination image tends to give us more opportunity for removing or finding similar pixels that can be blended together so as to do the denoising. It also allows us to filter more strongly without the risk of hurting the texture. After we have done the denoising, we can then multiply it by that texture image again to recover the original image with texture and all. The downside of this is it does mean that if you have any noise in your albedo image, that will be preserved because it's held out and then reapplied. So we can also do cross-frame denoising. So RenderMan is used for doing feature animation. So animation that's smooth and flicker-free is very important to us. So in this case, with the image, I've shown it with motion blur, and here is a camera move. If you look here along these grid lines, the horizontal lines, each one of these along the camera move is at a slightly different position vertically within the image. So those arrows indicate that. Keep an eye on those here. So the renderer can output 2D raster space motion vectors, which are its best estimate of where each pixel came from the previous frame and where it's going to in the next frame, based on the instantaneous motion of the camera and the objects involved, as well as the camera projection. So these give the best prediction. So using that, the denoiser can also try to warp the image so that the previous and the next frames surrounding the current frame that it's trying to process now register with each other. So if you'll note here, in the previous and the next frames, it has warped those so that those vertical grid lines are now in alignment with each other. And you also have sort of an occlusion reveal there at the bottom where there isn't data to show. So this alignment then allows the denoiser to blend the pixels not just in the neighborhood around each pixel, but also with pixels from the previous and the next frame. And that helps greatly to reduce the temporal flickering during animation. So now I've explained a little bit about why and how we denoise our renders. Looking at the big picture here, as you can see, there's a fair number of nested loops involved here, just looking at all of this at a high level. So this can make the basic denoising algorithm fairly expensive to run, though there are ways of parallelizing this. If you look at the code or look at this, there's basically what we're doing here is a lot of pixel comparison and a lot of pixel blending. And it's sort of an embarrassingly parallel problem here. So there's different ways of parallelizing this and vectorizing this. And so the initial version of the denoiser was already parallelized, but our friends at Intel have helped us to improve on that further. So at this point, I'll turn it over to Louis, who will talk a little bit about how they did that.
Thank you. And so when we started this project, we talked to Pixar folks, and they told us denoiser is kind of slow on the CPU. And so we said, okay, let's take a look at it and see what we can do about it. So this is one of the example data set that we used to analyze the performance of denoiser. And this is a multi-frame data set rendered from RenderMan. And each of these frames has multiple channels of data, like color, albedos, normals, and depth. Right? And each of these frames is about 170 megabyte in the format of OpenEXR compressed. So when you uncompress it, they are actually pretty big. And we use this as the input to denoiser in the cross-frame mode, because that's sort of one of the more sort of the default way they use it in production. So we want to make sure that it performs well in this mode. So this is 3 views from the Intel vTune amplifier. This is the tool, sort of the go-to tool we use when we look at application performances. And on the top here, it shows the CPU execution for 72 threads. And basically you're seeing like Andrew already said, all the filters are already running in parallel. So that's what you see these green regions are, but you also see a lot of sort of black gaps in between. That's because all the filters are executed sequentially, one after another. Okay, so well, each filter is parallel, but they are executed one after another. This is also true in terms of the emission types for the noise input. Right, we have the diffuse emission type or glossy emission type. All the filters for each of these types are also essentially executed sequentially. So looking at these gaps, you can see that it corresponds with the other view where it shows that we are only getting about 77% CPU utilization. And if you look at the lower part, the FPU utilization, these numbers are pretty small, so I'll just say them. So we get about 37 gigaflops, and this is fairly low. Consider that you could easily get a few 100 to 1,000 gigaflops on a single Xeons. Of course, depends on what kind of compute you're doing. And what's more important is the even smaller font over here that says packed gigaflops. And this is essentially 0 here. That suggests that there's really no SIMD operations in this application. And looking at the memory bound over here, although it's red, but we have digged into it further, it's not actually, this application at this point is not memory bound. It doesn't really affect the CPU execution. It's really keeping all the cores are busy when they are running in parallel. And on the left side, this is showing the sort of the hotspots, the functions that's really really are taking most of the CPU time when this application is running. So we can see, you know, there's one on the top there that's pretty dominating, right? 460 CPU time in seconds. And this is, of course, combining all the CPU cores. So our strategy to optimize this application is sort of going to attack it from two fronts. One is we really want to shorten the kernels, right? The filter kernels that's being run, which is already multi-threaded, but we want to enable SIMD, vectorize them so that they can run faster. And another front is we want to improve the parallel efficiency by reducing reduce or remove the serial sections in the application. And this can be done through overlapping the parallel executions among different threads. And I will go into each of these in these following slides. So here's an example of a filter kernel. This is actually being executed on a tile, as I showed, you know, that's being passed into the function. And so we are iterating through these pixels inside the tile and applying some operations on each pixels. It's important to notice, right, the input also have two Boolean value parameters, and these Boolean values are uniform across all the pixels. But because we actually do these conditionals inside the inner loop, we actually have to pay this branching cost for every single pixel operation. So it's important, if we want to achieve good SIMD performance, we want to reduce these type of branches as much as possible. And this is done through templates. Another important thing that we want to do for vectorizing the inner loop is to make sure that we can inline all the function calls. Right? This is one of the requirements to do SIMD, to vectorize this inner loop. And inline, even if you declare your function to be inlined, the compiler has the option to not inline them based on cost heuristics, right? And in fact, when we profile this in denoiser in vTune, we realize that some of these inlined functions that are not actually inlined. They are actually being called separately. So one trick to do this, to easily just force everything to be inlined, is use this pragma force inline recursive, right? Just put it outside the inner loop where you want to vectorize, and this will force all the function calls within that loop and all the functions that's being called by these functions to be all inlined. Okay, so this is a very easy thing to do. The compiler will help you to do it. And so let me explain this a bit more. So we did sort of a transformation on the previous filter calculation code. On the top here, we sort of rewrote that function using template, right? So originally these Boolean values as function parameters, we hoisted them out as template parameters. And because they are now template parameters, when you compile this, these conditionals become, instead of determining these conditionals at runtime, right, they become constant values at compile time. So all of these conditionals goes away, really, once the template values are defined. And with this pragma force inline recursive, this inner loop will have all the functions, these functions 1 to 4, all of them will be inlines as well. So to really call this template function, we have to change the original calculate function internally by declaring a static sort of function pointer tables, and call these functions based on the parameters, these Boolean values. And because this is all done at the compile time, so these functions are optimized for each of these scenarios. And the other benefit of doing it this way is that you don't have to change the interface for calculate, right? All the functions that's calling this function don't have to be modified. So with these two, we get to vectorize this inner loop. And in addition to vectorization at the kernel level, we are adding a nested parallelism to the higher level for loops. Right? In the filter, it's already parallel. All the filters applying to each tile in parallel. But we want to make sure these for loops, right, for each emission time and all the filters are also running in parallel. And this is actually pretty easy to do with TBB, right? But the challenge here is really modifying the code, the data structures, to ensure that we don't have thread safety issues, right? Because all the original code is using a shared temporary data and other buffers so that multiple filters can write to the same buffer and save memory. But because they are shared, we now have a read and write race condition when you run all of them in parallel. So we sort of really have to go through all the code to make sure that we cover all the cases, check them, and make sure they are safe. And then we can apply this very straightforward parallel for loop, right, on these two nested loops. And all I really did here, right, is using TBB parallel for. Once you figured out all the internals, right, make sure they are safe. This is a very easy to do thing with TBB. And because TBB is using task stealing scheduler, right, you just keep building up these tasks for TBB, and it will ensure that it has, keep all the cores busy without oversubscribing. So I'm using TBB parallel for here, but you could easily use something like a TBB task group, which is also very easy to do in this case. So let me just show some results. I have the denoise 21.4 are the ones I showed earlier in the slides, and denoise 21.5 are the ones that we optimized after we optimized, and it was released just a couple of days ago. And so you can see that we have essentially removed most of the gaps between these parallel regions, and the gigaflops, improvement due to vectorization is quite dramatic. We are going from 37 gigaflops to a total of 109 gigaflops, and the packed gigaflops over here is 87 gigaflops. So that's all attributed to the vectorizations on these top hotspots. And in terms of execution time over here, what used to cost 460 seconds now only cost 126. And just across the board, you can see that all these hotspots has improved by a factor of 2 to 3x. One thing I also want to point out is the memory bound, right? Like I said earlier, with vectorization, because you're working with more data, you're fetching more data, so this tends to potentially memory bound issues. We are not really memory bound at this point. It's pretty close. We're sort of on the borderline there, this was one of the factors that you see the CPI rate went up, right? The CPI rate is cycles per instruction. That's how, like how many instructions you are executing per cycle. And before it was below 1, right? It means that you are executing more than one instruction per cycle. But now we're at a little over 1, so it's taking longer, more than one cycle to execute one of these instructions. So another measurement of how well our application is running is looking at the scaling. And scaling is a very challenging problem because, for example, this using this data set, we measured about 1.5% of this runtime to be serial. Okay, and mostly it's in the loading of these EXR files. And even just this 1.5% serial section, when you calculate using the Amdahl's law, tells us that our upper bound is about 23x on speed up on a 36-thread system. That's pretty costly, right? You basically have 13 cores there that you're not really getting your money's worth. So what we got here is about 21x speed up, right? It's not quite ideal, but we're pretty close. And you may ask, why it's not 23? And there could be many factors contribute to it. And, I'll just mention one of them is, when you run single-threaded on a Xeon architecture, the cores can run at full speed, turbo speed even. And, but when you start to utilize all the cores, right, and using AVX2, you actually run at a lower clock speed than the normal turbo speed. So there's a speed, just in terms of the clock cycles, there's a performance difference there. So you probably would never, exceed this or reach that ideal scaling. After this parallelism, we are reaching about 13% is serial for this application. And this is sort of the final performance result that I want to show for this Sterling data set. On the left here is the 21.4 release built using ICC 15, using the SSE4 instruction set. And this is our baseline for comparison. Whereas the 21.5 release, using the same compile setting, we achieve about 2.5x speed up. And with the new release, now you can actually get the benefit of AVX2 as well. So if you are running on a system that has AVX2, you can achieve near 3x, 2.9x, close to 3x performance. So this is all what you can already see with the new release of denoiser 21.5. Just for for us Intel people that we want to see what's the best number we can achieve, right? So we built this built denoiser with the ICC 17, and with AVX2 we just everything is the same. The source code is the same. The compiler settings are the same. Right? Just by switching the compiler to ICC 17, you get better code generation, and you get up to 3.6x speed up. So all of these measurements are on the Skylake, the latest Skylake system. So we are, we are pretty happy with what we see here, but there's still places where we can improve. For example, as I mentioned, right, the scaling is the part that we really want to see improve, right? Because buying new hardware is not necessarily give you the money's worth of the performance. So really squeezing that 1.5 even further is what we want to see. The other challenge is in the kernels, where although we are processing these pixels in the axis, and the data are fetched in a unit stride. But when we look at the neighborhood for the filter functions, these are still gather operations. So these are all potential areas to improve. So with that, I'll give to Mauricio.
Thank you, Louis. Now we're going to have a Q&A session. Before we do that, I just wanted to have a quick call to action. The first one is if you have currently RenderMan, please upgrade to 21.5. It has all this code that we talked about and other optimizations. There are other great sessions from Intel. That's a detailed schedule. There's one coming up on open shading language that Alex and Max will cover. And we have some great demos, including RenderMan in action in Intel Booth 807. All the tools that our engineers have used and RenderMan uses are listed here. In case you want to optimize your code, that we have a compiler, VTune, 13 building blocks, and additional tools. RenderMan can be downloaded for evaluation. It's free for commercial use, and we have provided the link there too. So with that, we will be happy to take questions from the audience. Yep. Go ahead. I'll repeat the question.
Okay. Yeah, that was the Intel compiler. And what platform was it? What OS? Experimental OS.
So we
Repeat the question.
So I think you're asking what platform and OS we were running this on. So we run this on CentOS 7.2, but we also tried it on 6. I think that's what Pixar also uses. We have also run this on Broadwell system and Skylakes. So those are the platforms that we have run them on. These are all Xeon systems.
In the back. Go ahead.
Any benchmarks with AVX 512?
Did we do any benchmarks on AVX 512?
That's a good question. So Skylake is a fairly new Xeon system that's just released recently. We did have some internal benchmarks, but because we were working on this last year, and at the time we only optimized for AVX2, so I think for AVX 512 we need to do some further investigation. So I don't have really a number right now.
Any questions for Pixar? Yeah, right here in the front, please.
I'm just curious if you're thinking of taking a similar approach for other areas.
You want to repeat the question?
Hello?
It's a,
Okay. Yeah, I mean, a lot of these opportunities here are sort of some of the lessons we've learned on, like, just how to work better with the Intel compiler as far as producing, like, SIMD vectorized code are applicable to other parts of the renderer. RenderMan operates on batches of points. We've got various places within it where we're able to work on batches of data in sort of a data-oriented fashion a little bit. So some of these could be applied there as well, I would say.
okay, thank you. You had a question too?
Yeah, what you did with the constant hoisting, it seems like a good technique, but it also requires some slightly tricky code change. You have to write an explicit dispatch column, the right version of the template. It seems like something a compiler ought to be able to figure out. Perhaps with a little hinting to say these are good parameters to do that to. Is there any plan to look into doing that?
I guess the question is, can the compiler do some of the things that you suggested, Louis?
Yeah, all that Alex answered that more, but I'm not aware of any of that.
Yeah, I think some of this comes down to the language itself, and that great, maybe we should submit something. I'm not sure Intel-specific feature to do that would serve the community best, because you can do it by hand. It does work on other, that is not an Intel compiler-specific trick there. So maybe this is something to take to the language committee and say, hey, can we do this, because it is a little bit of a pain in the butt to go do it by hand. Although it's really simple, you got it on one slide, so.
In newer C++, there is attributes and you can use to attach information, so maybe there'll be a way to do that.
Yeah, your compiler would have to do something with them.
Right.
All right, anybody else? All right, one question.
Since every Intel CPU, like for home system, comes with a GPU, so why don't we use the GPU?
Want to answer that one? So why, if some systems come integrated with GPUs, why not use the GPU as well?
Come to our event tomorrow night. That's all I can really say about it right now.
All right, last question. Don't be shy, one more. All right, let's give a round of applause to the presenters. Thank you. Thank you so much for coming.
Hi, let's get started. Welcome, I'm Larry Gritz, and we're giving this talk jointly. I'm at Sony ImageWorks, and we're giving this jointly with Alex Wells from Intel and Max Liani from Pixar. This is a collaborative project here. There we go. All right, so the idea here is to give you a brief introduction to OSL. Although looking around the room, I think most of you know what it is, and talk about sort of where we've hit different limitations and an exciting project to try to adapt it to newer computer architectures to take better advantage of what they have to offer, and some actual code that's been written to do this. So briefly, just in case anyone isn't familiar, shading is the part of the 3D rendering process that is concerned with making material appearances, whether something looks like, wood planks or rusty metal, concrete or cloth or whatever. This is result often of some computational process, and it can be quite an expensive part of the rendering process. The way this is usually addressed in high-end renderers is through some sort of system where people can programmatically describe the properties of these materials in shading languages. At Sony ImageWorks, we developed a new shading language to do this that, by virtue of being kind of a fresh design, was intended to take a big step forward from some of the previous languages, and in particular, be a little bit more suited to the kinds of physically based lighting and shading and a more ray trace oriented rendering paradigm that all of the renderers were starting to converge to, which is really quite different from the underlying architectures that had been used when most of the earlier languages really had their origins. And we have made this an open source project. And as a result of that, it's not just something that we use internally, but it's been finding its way into a large number of commercial products, open source products, and as well proprietary rendering and other systems at different visual effects and animation studios. And so it's a good place to leverage some of the technology and advances in the hardware. If we can make it OSL more computationally efficient on those architectures, that can actually propagate its way out to a whole bunch of products that people use. And because this has been so influential, earlier this year, this work was recognized by a SciTech Academy Award. So we've got some good publicity around this these days and a nice wide adoption. OSL has already been used on at least 60 or more completed films, and I know a minimum of another 16 at least that are in progress for later this year or early next year. So again, wide influence of where any steps forward we take can get applied. So OSL was really designed to, in particular, take a step forward for more physically based renderers. And so it's used to both program pattern generation as well as all of the inputs that come into to the descriptions of the material properties themselves. In OSL, one of the things that distinguishes it from previous languages is rather than computing a single view dependent color, for a particular viewpoint coming from the surface, which was usually in the wrong physical units anyway, instead it's got a more functional representation called the closure of what's going on the surface that is view independent, and rather than computing a final result, it's like a little bundled set of functions that can be passed back to the renderer and then used to more intelligently sample, evaluate, and integrate. And architecturally, what we're doing is there's a pre-compilation step that happens offline where we compile the OSL source code into an intermediate representation, but then at runtime, as we assemble these into big networks of shaders, once we know what all the connectivity is, we JIT the whole thing into x86 code, and we're using LLVM for that. So, like I said, some other systems have used like these big monolithic shaders, essentially like it was one big function that implements the whole thing, and OSL, as kind of a first-class concept, assumes that the material is described by, basically a DAG, right? A tree of these, individual shader nodes, each of which is a program with outputs of upstream layers getting connected to inputs of downstream layers and a final result coming out at the end. And these things can be really quite complex. So inside one of those individual boxes is a little program in a C-like domain-specific language. It should look relatively familiar to people who are familiar with, C, C++, Java, that sort of language of that family of syntax for programming languages. And there's a bunch of ordinary math. There is also calls to standard library, kind of calls, library functions, and references to both parameters to the shader, as well as what we call global variables, which is really state about the point that we're shading, the position, the surface normal, surface parameters for texturing, that sort of thing. So the steps we go, as I mentioned, there's an offline compilation to a machine-independent bytecode, but then that's for each individual node. And then at render time, inside the renderer, these are being assembled into the big material networks. So lots of nodes are brought in, the connections are established, the particular parameter values are bound, for different free inputs. And then at that point, we know a lot of information that wasn't known at sort of the original compile time. We know all the specific values that previously were variable parameters. And with this knowledge, we perform this runtime late optimization pass on the network as a whole. And it's very smart about turning all those bound parameter values into constants, letting those propagate through all the computations, doing a ton of constant folding and other optimization on it. And as well, because it knows the connectivity of the network, it really can understand a lot about which bits can be optimized away or turned into something less computationally intensive. The result of that pared down network is then turned into LLVM intermediate representation, run through the LLVM optimizer, JITted all the way to machine code, and the result of that is what's actually executed, on a point-by-point basis. So this is it's an open source project, and the way it appears to the render implementers is as a runtime library. So there's a very small API that the shading system presents to the renderer to say to declare the shaders and connect them together and cause compilation to happen. And there's a corresponding API that the renderer presents to the shading system that we call renderer services, and that's all the things that the shading system will need from the renderer, like asking for texture handles or the named lookup of transformation matrices, that sort of thing. And so there's those two well-defined APIs are the sole communication channels between them. And so this makes it super modular and makes the details of the internals of the shading system and the internals of the renderer very decoupled. And that is partly what allows this to easily get integrated into a number of renderers, which often have quite different architectures underneath. The result of all the runtime optimization is, at least at Sony, that our experience was that because of the degree of optimization we could do on those whole networks, we actually got to the point where the execution of the OSL shaders was actually faster than the equivalent of precompiled C++ shaders in the old system. So let me say a couple words about complexity. This is an example from a movie that we're working on right now, and I want to give a few statistics, basically just to boggle your minds a little bit about the scalability that we have to deal with in systems like this in this kind of high-end film production. So this is a final composite. So there's actually a few different separately rendered elements and a little bit of compositing magic. So the stats are just about one of those elements, but it's pretty typical for the scene. So there are 8.9 billion triangles in this scene. There's a lot of instancing, but it's still 300 million unique triangles. It renders in about 22 gigabytes of RAM, and one of those elements took 16 core hours to run. We run these multi-threaded, of course. It took 85 billion rays, and if you do the math, that's 15,000 rays per pixel. So we sample like crazy, and there's a lot of rays involved, so that's why these frames are very expensive. And in the course of this, the shaders had to be invoked 173 billion times for this image element. So those shaders, in this scene, there are almost 3,000 different materials described by shader networks, and a total of 237,000 plus individual nodes means that on average, our materials are a network of about 80 nodes, sometimes a little less, sometimes disturbingly more, but they're pretty complex shader networks. And just to give you an idea of the crazy complexity here, there were 324 billion texture lookups for this, which is 52,000 texture calls per pixel. You do wonder what it's doing for all of that. There are over 8,000 unique textures in the scene that total 77 gigabytes on disk, but that's compressed disk files. It's actually uncompressed. If it were all loaded into memory, it would be 174 gigabytes of texture. Just to give you the flavor of the size scenes we're dealing with and why this kind of optimization is so critical to keeping the times from being astronomical. And so the runtime optimization that I was referring to, all those materials that came in started out as 280 million instructions with 161 million symbols, and that got optimized all the way down to a mere 2.5 million instructions and 2 million symbols. So that's pretty big. And of all of those instances, actually almost 2/3 of those, by the time optimization was done, was actually reduced down to pretty much nothing. Great. And now I will turn it over to Max, who will expand a little bit more on the production complexity and the issues, why the issues of trying to tame this complexity with hardware is so important.
Thank you, Larry. Yeah, Max Liani, I work at Pixar. Like a bit over a year ago, we started this project. We have a production renderer. It uses C++ patterns and uses open shading language as well, because it's a very popular and very versatile language. But we got like some interesting results out of like testing. But before I get there, I want to explain a word of what production renderers are. So production renderers, as Larry was pointing out, are these like complex machine that turns like complex data sets into pixels. And what is thrown at those production render usually tends to be pretty big. Often these assets are not optimized because the production times are so constrained that artists don't have the time to really figure out exactly what is the optimal combination, both in terms of geometry representation, texture, and shading. So like everything gets jammed together, thrown at the machine, and we have to do the magic in our side to make things as fast as possible. So these production renders are equipped to be versatile to do a lot of things, a lot of option parameters. They need to be highly scalable to like manage this like crazy amount of complexity that is thrown at it. And one like traditional technique to get this thing to scale is to use multi-threading. So you get every thread to run like computer an individual tile of the image, like a bucket of the image, and that's like so far so good. There are like of course like a scalability issue when you are running into like very high core count, but it's like established techniques and not something that requires a lot of research. But the demand is constantly changing. We have bigger and bigger complexity that we have to manage, and the technology is changing as well. So we don't only have more cores or more machines in our farm, but we have wider SIMD units in those fast chips that we have to make the best out of it. So some production renders these days are vectorized, like RenderMan is vectorized. It uses small batches of points, and it tries to do SIMD computation on those, or trying to extract coherence and and locality in the type of computation that it does. Hyperion from Disney is like the Disney production renderer is another like example where that type of like batching vectorization is taken to the other extreme end, where you have like very large batches, millions of points, GLs at a time, and other renderers are going this direction too. So there is an extensive effort to leverage the hardware in terms of both multi-threading and vectorization. And as part of that, the shading system is a big part of the renderer. So we have to do, like shading is relatively, like is trivial to vectorize because you can run shader execution on all threads. Of course, when you're doing texture lookups, there is texture caching that gets in the way of scalability, and that's like a problem. But what about vectorization? So writing a C++ shading system that is vectorized is much more complicated. So if you ask your users or even your technical user to write vectorized code, it's not pretty landscape. And they do lack that sort of optimization that Larry described before. Like you have like a complex shader and the static compilation that happens when we package and ship this tool is not going to be able to optimize parameter use, and it won't understand a network of shaders and the connectivity. So, and also, like if you write a C++ shader, it's going to be bound to your system and not be reusable across different rendering solution. That is a desirable property these days. So on one side we have an increasing complexity, and there is a lot of research, a lot of papers that lately, like for a number of years, they improved massively ray tracing, which is like used to be like the dominating portion, at least for a patch tracer, it used to be the domination portion of the computation, and now ray tracing is substantially faster and more robust than ever been. In the other side, shaders are getting more complex, and we don't see the type of transformation or revolution happening in that domain that makes them dramatically faster. So it turns out that these days in production, production rendering, you might have majority of the time is actually spent shading rather than tracing rays, and OSL runtime have this great potential of reducing that shading complexity by folding away and removing static code paths and all the things that the user didn't want when he put together the shading network. So what, like on the plus side, at the beginning I was saying that like in Renderman, for example, we have both C++ pattern and OSL pattern. So in a C++ shading system, we can do execution of batches, we can leverage vectorization, like a SIMD execution, and as another benefit, we have like a good debuggability of the software because we can, put a breakpoint, check what's going on, check the registers, but we don't have any of those runtime simplification. And if you look at this image here, like if any of you use Maya, you probably recognize that 2D text replacement node, and it's there in every shading network. You find dozens of those, one for each texture layer, and often none of these parameter changes. They are set, they are constants. If the user does something, plays with one or two of those, despite it, if you have a C++ shader, is going to compute all of this stuff all the time. So maybe you can wrap things around conditionals and say, rotate frame, is it 0? Then don't do this. Don't do the transformation. Still, the conditional will run, and that incur into like costing of red. And the more simpler your shaders are, the more you incur into this cost. So in the other side, we have open shading language with all these great benefits, but it's single point execution, so it doesn't allow us to leverage SIMD that well, or at least it does. In terms of block vectorization, there are it turns out that when you have like a regular production shader, a fair amount of the time is spent evaluating noise patterns, like procedural noise, like Perlin noise, Gabor noise, simplex, and so Larry and his group did like extensive work on the past to do vectorization on those patterns by doing, let's say, 4 octaves of Perlin noise at once. But that doesn't scale with the like modern hardware where the SIMD width is 8 wide or 16 wide. And this brings us to, can we do both? Can we combine the benefits of the two systems in one new backend? So I'll pass the mic to Alex Welsh.
Howdy, I'm Alex Wells from Intel. So we've been working on this to try and get this going. And so looking at a vectorized OSL, we want to use like single program, multiple data techniques. And our biggest thing is we don't want to change in the language itself. So we want all the shaders and all the way those are specified to stay the same. We want to leverage the existing great render time optimizations Larry was talking about. And really, we want to create a new wide path so you can submit a batch of data at a batch of points at a time. But we'll retain the existing single point interface because this may not apply to everything. Along with that, if we have a way to submit a batch, we're going to need a new backend to generate some vectorized LLVM. So it sounds simple on the surface, but there's a lot of devil in the details we'll get into. So first is sort of the wide interface. So the renderer may or may not have some large shading batches. We prefer in ISOs with points at a time, but there's this what width to choose. We sort of decided initially here just to shoot for 16. Let's submit 16 at a time. It's a compile time configuration, so it can be changed. But we wanted to get out the door and discover all the issues through the rest of the pipe and not be stuck on what the front end should look like to handle every possible scenario. So the way this looks like, if you're familiar with the OSL shading system, is you build up a shader globals, and that's all the global data about the point you want to push through the shader, and then you call execute. Afterwards, you can get a symbol address and actually access the data for one of the output parameters you might be interested in. So we just basically added some new batched versions of those, and you can see the just batch on the end of them. And instead of a shader globals, now we have a shader globals batch, and that's going to represent a whole batch of data. Once it's done running, it's got results for all those, so we had to make a new way to get the results out. So instead of a symbol address, now there's a batch accessor, a symbol batch accessor, and it gives you this output accessor that's actually type specific. And with that, it's sort of like an array subscript. You can access element 0 through 15 to get at the result data. So what's actually in the shader globals batch? So we took the existing shader globals and sort of split it into two. Some of the data members are uniform, like render state, trace data, object data, context, the renderer pointer. Those are going to be the same across the entire batch. Other things, such as the position, the instant ray, the shading normal, those may be varying over the batch. So we separated them sort of into two groups, and then we made this shader globals batch, which has both. So you can access the uniform portion, or you can access the varying portion. Now, the way this works is it provides a proxy to the varying portion, which is basically a view on the next slice of varying data you want to submit. So you go through this varying proxy to set values, and once you've populated it, you can commit it. So this is sort of like, the commit's sort of like a push. And so you can iterate through this and build up a batch, and eventually your batch is full, and you know it's time to actually execute it. So how do we represent the varying data under the hood? So again, this is under the hood, so you wouldn't necessarily see this directly. We use some techniques from the Intel SIMD data layout templates, inspired by them, and created wide wrappers around them. And so this is basically, here's an example of a wide version of Vec3. It's got a fixed size array for X, Y, and Z. Now there's proxies around these, so when the user's working with them, they don't necessarily see the wide version. They just work with the Vec3, and when they submit it to the batch, it gets placed in the correct data lane in this wide data structure. So it's sort of transparent to the user, lets them continue working in the existing data types they're used to. So rendering a batch is different, and so this is one of those changes to the renderer to take advantage of this, because instead of a single point, now we got to build up a batch. There's a lot of stuff here. We don't have to go into all of it, but basically you have a shader globals batch. You want to set up the uniform portion of it, and sort of a exploded view of that is we can access the uniform section and assign the render state, the rate type, etc. There might even be some varying values that you want to make uniform across your batch. Well, you can do that too. So once you've set up the uniform portion, you're going to want to iterate over your samples that you want to work with. And for each of those, you want to set up the varying shader globals for those. So those are typically your UV, your position. And so here we're just accessing that varying proxy and doing assignments to the U, the V, and so on. And once we're done with those, we can commit that sample to our batch. Now, back here, eventually, our batch is going to be full, or we're going to run out of samples to add. At that point, we talk to the shading system in OSL and ask it to please execute that batch. It does its magic. Afterwards, now we can iterate through our output symbols and grab a symbol batch accessor of the type we care about. And this is one of those proxies where we can just walk over the indices here, doing an array subscript, and lo and behold, we get a Vec3 data out. So again, it's hiding a bunch of that. And then after we've processed all those results, we can clear our queue of our shader globals batch. We can clear it, so we're ready to start adding to it again. So that's just sort of the flow from the render side to use this new interface. So now that we've handed a batch of data to OSL's runtime, how's it going to process it? So we want to do this in this single program, multiple data execution manner, and we want to emit LLVM. It already was, but now we want to use the vector types. So we're going to emit LLVM code directly as vectorized code from LLVM's point of view. But we have to take on the work ourselves to manage all the per lane control flow divergence from for loops, conditional if statements, else's, early returns from functions, and so on. That's only part of the story because there's all those built-in library functions, the noise functions, the absolute value, there's some 400 odd different combinations of functions in there. And those aren't actually in LLVM, in OSL's library. So we need wide versions of those that handle masking as well. But then once we do all that, we can let LLVM generate the actual, lower it down into actual x86 SIMD code. So to get there, we had to upgrade LLVM to 4.0 for the OSL project, and that's mostly because we want to be able to target AVX 512, also a lot better code generation happening in that version of LLVM. Again, we're going to generate code directly as LLVM vector types, such as 16x float, that's sort of the LLVM type for most of it. We add a new system to identify uniform and varying variables automatically, and we'll talk about that. And anytime we mix and match those two, we can promote uniform values to varying when they're used. And we had a lot of issues to resolve data alignment because we're literally taking that batched data that's already in a SIMD-friendly format and having LLVM code generated directly against it, so we don't have an additional data transformation step. Okay, so identifying uniform versus varying variables. So because, unlike a traditional language like C, OSL is a domain-specific language, and we know exactly all the inputs and outputs to all the library calls. So we know exactly what is going to be modified by which call. So we can actually analyze which variables are connected to varying shader globals and which are not. So in this example here, this variable P is the position from, it's a shader global, and we know that's varying. So we can actually trace it through and see that causes P shade here to become varying. P shade's used in this noise call, so we're going to call the wide version of noise. We know his result will be varying, and so on. However, we notice this loop control variable I isn't influenced by anything. So we know it's going to be uniform across the batch. Same thing with this frequency value here. And this can save us a lot, especially on control flow logic. We don't have to deal with any masking because of this loop, for example. And this is also true for the callbacks through render surfaces. They're well defined, so we know what will be modified and can apply this all the way through. So it's something we can't do easily in an open language like C++. So how can we handle divergence? So we can, if we do a conditional operation, if we do a vectorized version of it in LLVM, we're going to get back a mask. Basically, we get true or false back, 16 of them. So 16 by a 1-bit integer here. So great. How can we use that? Well, we can use a select operation, and we can give it an original value as well as a value that was built inside of a conditional branch. And that'll, based on the mask, select either the original value or the branched value for a result. So we got the mask from the conditional operation. The original value, well, we could have just load that from its place in memory. And then this value assigned in the branch, we had to basically store separately. But where do we get that mask when things get complicated? So we actually keep a mask of stacks. Starts empty, but as we hit conditionals, we start pushing their mass onto the stack. So as we hit the second conditional here, it gets pushed on and it's ANDed with the previous result, and so on. So at any point, we can go to our stack and know what mask we should use to do that select blend operation. And then as we leave conditionals, you'll see here we pop off the stack. So, and then possibly when we hit the else case here, well, we have to push on the negated version of this conditional here. And then as we move down, we can see we continue to pop the stacks off, or pop the mass off the stack. But do we actually have to use those masks everywhere? And the answer is no. We try and minimize where we use the mask. So this is a little bit complicated, but basically the idea is every time there's an assignment, we can track which mask from the stack was involved at that point. And it's only on the reads. So in this case, here's a read of G, or that's a write of G. Eventually we get out here, and here's a read of that G value, and we can see that the mask at the point of the read is not a subset of the mask from when it was written to. So that's our indicator that we need to go back and change these instructions, these assignments, to use masking. And then, for example, here's this result RGB. Even though it's not read anywhere else, when we get, because he's a output parameter, we treat it as an implicit read and know that, oh, look, he was assigned inside with a different mask than he's being read with. So we're going to have to go back to that last write and turn on masking. So if you look at this here, we don't actually have to call a masked version of smooth step function. We just need the result that's being assigned to use masking. So we can try and, minimize the amount of masked instructions we're actually emitting here. So another thing we did is we enabled profiling and debugging, because we needed to basically see if the code we were generating was what we thought it should be. So this actually ended up not being too bad to do. The LLVM already has a special flag you can set when you're building to turn on JIT events. And then we modified the OSL source code to emit LLVM debug information. So now we can profile, we can map the OSL to the assembly view in VTune, and with some extra work, you could even get it going in GDB some. But just as an example, here's that same shader after JIT in VTune here, and we can actually see this line of source code is mapping to these generated assembly instructions, and we can see time spent and so on, which is kind of handy. So now with that there, I can actually see where the time is being spent in VTune for that little marble shader. And looking here, this _2, this is the actual LLVM JITted code. This noise FV, well, that's the noise function that was being called from that JITted code. And we can see we're spending 95% of the time in the library call to noise versus the remaining 5% or less in the JITted code. So it's a big indication that we need to do more than get good JIT. We need the library calls to scale well in SIMD. So the noise calls, for example, that are used in this shader, there's a bunch of different options, Perlin, uPerlin, Simplex, Gaber, and so on. They're pretty complicated, full of hashes, lookup tables, gradients. So the strategy we took here was to use explicit vectorization of the outer loop. And we did that with the Intel C++ compiler using the OpenMP 4.5 standard, which sort of boils down to this Pragma OpenMP SIMD. But part of this is we needed some C++ code to work on, and a lot of this had already been written to SSE intrinsics. And then also we had to do some hand tuning to make everything happy. But to get an idea of what this looked like, so this was sort of the code that was getting called for the Perlin scaler here. And again, it was using just working, computing one result at a time, but inside it was doing a bunch of hashes, and it says, oh, look, I can work on X, Y, and Z and generate those hashes at the same time using SSE intrinsics. So we actually sort of had to take that and make a non-intrinsics version that was just sort of, de-optimizing that to get back to original C++ code, so we call that Perlin scaler. But it's the same algorithm that it's doing. It's working with the X, Y, and Z, doing all the hashing and other fun lookup tables. But now, in our new version here, in the batched version, we're working on that wide data. So we have a wide accessor to a float and a wide accessor to a vec3 versus just a float and a vec3. And so we got 16 things, or with T things, we're going to be working on. So we just iterate over the data lanes, we extract a vec3, we call our scalar code, and then we get our scalar result, and then we assign it to the result in the correct data lane. And right here is our explicit vectorization. We're explicitly telling it how many data lanes we want it to vectorize on. So it's able to take the scalar algorithm and then just apply it across all the data lanes at this loop right here. One of the things we did to make sure there were no surprises around inlining is we use this extra pragma here to tell it we want everything in here inlined. So what's made it, when you actually compile the code, it produces some strikingly good SIMD code, and we can generate it for many targets, AVX, AVX2, AVX512. So sort of looking at this before and after, this is the Intel Advisor tool here, and this is probably way too small to read, but the upshot of it here is on the original version, we could see that it was vectorized using XMM registers limited to 4 data lanes, and we could look at the _2 function and see that it had no SIMD. So the noise function was using it. But that was that block vectorization. In our after here, we can now see that it's using AVX512. And we can generate for 4, 8, or 16 floats at a time. We can see it's using fuse multiply adds and subtracts. And we see this wide 2, which is our JITted version in the wide, is detected as using AVX512. So now if we look in VTune again, we can see our JITted code here, this _2, is 13 times faster than the previous version. The noise function is 4 times faster than the previous version. But remember, the previous version was already operating on 4 data items at a time. Now we're operating on 16, so 4x is sort of the limit on that speed up there. So you put this all together and look at some initial results here. So for that, this is running on via Test Shade, which is a test harness that's part of OSL. That marble shader is overall 4.2 times faster. This is an oak shader. It has a more complex control flow. It's got a break and some for loops and some other fun stuff going on. That's about 4.8x times faster. This is a 3-node network put together with a whole lot of noise calls, and it's about 3.3 times faster. And this is a 29-node network that's used to do all the shading on this ground plane and this statue here. And it's using the very expensive Gaber noise, and it's running about 9 times faster. I don't think that one was vectorized with SSE intrinsics, which is why it's appearing as a larger speed up than the other ones. So the starting line was different. Now, these were all compute-bound things. What's going to happen in a real shader that involves tons of stuff? So just as sort of a sneak peek of how far we've made it with this, this is a 300-node shader network from a production for the Fillmore character, and it's just running the shader network in Test Shade is running 1.4 times faster, and that's with a texture subsystem that has no improvements for vectorization yet. So I'm actually surprised it's that high. So you know, we're hoping we'll be moving on to looking at texturing. Larry's working on some of that right now. So we're hoping all this comes together very nicely. So our next steps is trying to get covering all the built-in library functions, looking at the generated code and making sure it's optimal, looking at different target WISPs. We've been looking very much at AVX512, but we'll want to make sure this works well and generates correct code for AVX2 and so on, especially around all the lovely conditional masking code. We're going to experiment with different batch sizes and explore this MD texture system. And if we have batching, could we possibly split this shader up and, you know, hey, let's run 1024 instances up to the first texture call and shove all of those through the texture subsystem together. So starts opening the door to do some more exploration, and you know, with actual production data being embedded at Pixar, we hope to be able to make some good decisions on some of these things. And we'll be contributing all this back into the open source. Future release of RenderMan will be looking to integrate this. And here's a whole lot of different resources on this. In particular, the actual, if you just Google OSL, you'll find the GitHub site on it if you're not already using it. as well as how we did the vectorization with the OpenMP 4.5 for the library calls. Okay, and I think, yeah, I'll just leave it on the resources slide and open it up to questions. Rasmus?
So the visual text reference platform specifies that this community likes TDD. TDD and OpenMP don't mix very well.
Right, okay, I'll jump to that. We're not using OpenMP threading here at all. So OpenMP has a threading standard, but it also has a specification for enabling SIMD. So depending on your compiler, we have a flag -Q OMP SIMD. I'd have to look it up to be exact. But basically it just turns on the standard for the SIMD clauses. You could have done this without the OpenMP SIMD. The Intel compiler has all of its own compiler extensions for SIMD, but we've taken those, worked with the standards committee to integrate them to OpenMP, so it's part of an open standard rather than a Intel specific thing for vectorization. So I believe GCC and future versions of Clang will be supporting these if they aren't already. Yeah, so you don't, none of this, none of the results have shown use really any threading. It's assumed the threading is being handled at a much higher level in the render.
Like, absolutely, like OpenShading language do not assume anything on the threading side. Like there are like context.
At a higher level, right?
Yes.
There's multiple things being shaded at the same time by different threads, but then within the shading execution, it's assuming it doesn't want to fan out threads because they're already being used elsewhere in the renderer. So
I just wanted to make sure you weren't pulling in a dependency that
Yeah.
is going to set up something else.
And just a,
very hard not to.
yeah. And just a note on, just a note on OSL itself is already set up very nicely to handle multiple threads. It doesn't thread itself, but it has contexts and other things set up so you can use it in a threaded program nicely.
I'm pretty intrigued by the debugging work you did to bring OSL through to can you talk more about what it's like to actually take a, it looked like you had a production OSL shader that you were able to analyze there. Is that something that
Well, it depends on how you build OSL. So you need to build you need to build your LLVM dependency with that flag.
Sorry to interrupt. You mean building LLVM itself?
Yes.
Oh.
So if you just grab LLVM and install it, it probably won't show up. But if you grab the sources and just, that's the only addition is that one flag, then that'll generate the hooks in LLVM to do it. The other part is in OSL, we have to generate correct debug. We're generating correct enough debug for the one shader. Life gets a little interesting when the preprocessor gets involved as far as it's still there, but it's sort of like inlining in C++ where, you know, getting the right source line associated can be challenging still. But
it's going to be even worse when you consider the optimizations that are happening before we, you know how like in C++, if you turned your C++ compiler optimizer up pretty high, like you can lose the correspondence between, you know, what your original source code looked like and generated. It's probably going to be even worse here. So this is more like for compiler writers than end users in terms of the debugging.
But well, here's what I can tell you you will get if you do this. You will get, for each LLVM generated function that's callable from the outside, so when you execute a batch, that function will show up in your, in vTune. And you'll get the assembly with it. And you'll get some association to source lines. That's where, it's the association to source lines that could use some more work. You got any free time? Okay. Yeah, even just to tell how much should we speed it up by, rather than just having this big, unassociated calls, now we can see it.
so you actually run
Yes. Thanks, Max.
I'm interested in, I understand that the Perlin noise is still a scalar function and just gets called multiple times depending on the width of the register. It gave you a very good speed up. How come you didn't get the same with the textures?
Oh, we just haven't done it.
We haven't done the texture yet.
But the Perlin is still a scalar function too.
No, it's actually.
Scalar too, so why the difference?
So the question is why we got like a good speed up of something that looks like a serial execution of a Perlin noise and not from a texture. So the code that you saw there looks serialized, but the pragma at the top tells the compiler this thing needs to be turned into like a SIMD execution. So you write serial code that looks like very simple to go through and very simple to understand, but then it gets widened to the SIMD width that is determining a compilation time of the library. So in our case was 16 wide. So the Perlin noise was running 16 wide. While the texture lookup, because we didn't get this far to do that work, in that case, yes, there was an outer loop that was going sample one by one, and that is why in that case on a shader that was like doing I don't remember how many hundreds of texture layers, it was bottlenecking on the majority of the execution time was actually serial code, and that's why like there was a very small speed up, but we expect a very big speed up coming from when that work lands.
I was confused with the scalar name, so it actually becomes SIMD code.
Yeah.
It was just written in a scalar fashion and let the compiler do the work. Okay, I get it.
Yeah, if you try and SIMD a loop and in the middle of that loop is SSE2 intrinsics, the compiler goes, what do you want me to do here? So, but if it's just C++ code that's inlined, I'm amazed at some of the results it's getting here, as well as even the LLVM JIT code is for AVX 512 is strikingly good that it's spitting out.
This may be, if I might ask another question, maybe more an OSL question than a Troy question, but why the difference between render callbacks and shader globals? Isn't it kind of the same thing? And what makes one thing a callback and what makes another thing a shader global? And are the callbacks then also in SIMD? You have to provide SIMD results.
Yeah. Repeat the question? Or part of it?
My eyes don't read things that small anymore. So the first part of the question was why are some things global state and other things are renderer callbacks? And yeah, I mean, some of that is historical artifact or arbitrary choice or just, we picked sort of the core. I think we picked the core things that every shader is going to have to touch, like the position that you're shading, the main, UV coordinates on the surface, the normal, and just a small handful of other things, and said, that's just the named global state. There's it's always called P, whatever. And then there are a bunch of other things that might get accessed by some shaders, who knows? And for those things, there are renderer callbacks to get them. And often those are they're not always, trivially, it's harder to figure them out. Like sometimes the renderer has to do work to figure that out, and you don't want to do it ahead of time. Like you're going to need P, so you fill those slots in before you start the shader, right? But if somebody asks for some weird transformation lookup or whatever, some shaders will do that, some don't. The renderer's got to rifle through stuff to find it. So those became callbacks. And so the second part of the question was, what about making those wide? And yes, right. So part of this work, which isn't all done yet, this is preliminary, is to go back to that renderer services layer and make wide versions of all those different ways that the OSL system might have to call back to the renderer, and so the renderer will then also have to supply, the other half of those wide lookups, right, for those things.
Yeah, I didn't have enough time in these slides to get into it, but on top of that execute batch, the render services, there's now a render services batched that has wide versions of all those render surfaces call. And similar to this noise one here, you know, whereas maybe the render surfaces call had a VEC3, now it takes a wide VEC3. And there's even a fancy masked reference that's sort of a type-safe version for writing outputs, and it transparently has the mask embedded in it, so you can write to a data lane that's masked off and it'll just ignore it. When it's all inlined, it actually generates some pretty good code. Although we're expecting these callbacks, whether the renderer can actually implement a SIMD version of it or not, who knows? It depends on the renderer. But we have a transparent way to let you work with the existing data types just going through these proxies. And again, you're writing directly to the memory and the JITted code there in a SIMD-friendly format and is ready to go on. And, you know, I can already say from one renderer that's been playing with this, pulling results out is actually much faster than the previous version. If you had not a SIMD version of any support function, you might be faster just from 1/16 of the function call overhead from all the chitter chatter back and forth. Yeah. And
also on that line, often when you search for, like you're accessing attributes and other things, like you might have to do search into an attribute state of the render, whatever data structure you have. And in this case, you know that the name that is going to be searched, like the attribute name is constant, uniform. So you can do the search once and populate that value for like the 16 wide. So there is a substantial speed up that comes from there, from production shaders. Another thing to like add, I don't know, I'm not sure if it was like came out clear, is that in this project we didn't want to change the language at all. We want to like just get exactly OpenShift language the way it is, just wide.
So I think I follow what you're doing with the masks to track when you have conditional code. For C++ code, when you use the pragma SIMD SIMD, does the compiler do something like that automatically?
if you had a mask. So the compiler internally, anytime there's a conditional statement, does something similar to what I'm doing. What I'm doing is directly at the LLVM level, and because I'm working directly with wide data types and LLVM intermediate representation versus outer loop vectorization. So the compiler is doing sort of what I'm doing here. The compiler, the C++ side of things, they have heuristics for deciding whether they want to always execute a branch and blend the result, or if, well, should we test all the data lanes to see if it's zero and jump? And to give an example, at the LLVM side here, when I'm generating it, I have the same decision to make. Do I execute both sides of this conditional and from the OSL shader, or do I do a test to see if all the data lanes are zero and skip this? And I can tell you a month ago, I executed both sides, and now I always test. And, you know, next month it'll probably be a heuristic.
There are a million little, not just for this project, but I've always found any time, you know, either threads or SIMD is involved, there are a million little details like that, and often not a lot of intuition about the right way to do it, other than to implement several ways and benchmark them, and then you eventually sort them out one by one.
Mark.
Hey, so this is a question for you, Alex. So you were saying that you do some analysis to see whether, to automatically detect whether a variable is uniform or varying. And so I was wondering, is that, by the time you look through the program, is that the exact categorization, or is there any heuristics, or you're being conservative with, you know, estimating what's varying?
It's exact-ish. So some of this comes into when a variable is reused. Let's say in the first half, it's only used by uniform assignments, and in the second half, it's assigned varying. Right now, I'm taking the easy way out, and if anything touches it that's varying, I promote it to varying. Technically, at some point, when this analysis will hopefully move up from where I'm doing it to higher in OSL land, and some of this comes into when OSL's front end analyzes the symbols. One of the steps is, great, let me go combine all these symbols and try, what I need is a clear separation that, basically two versions, so if P shade maybe earlier was uniform and now is varying, I want two P shades. I want a P shade, and a P shade prime in the symbol table to play with. So we can be very exact, but that's one of the things, non-perfect things right now. Ultimately, we're discovering getting the rest of the library and everything done is more important than micro optimizations.
Once we have it all working, there's a lot of time to try to optimize it more. But also, I have a theory that I don't know if we have enough data to bear it out yet, but which is that, in an old style shader where you mark things as uniform and varying, like there was a lot of uniform stuff that you really wanted to exploit. My theory is that because of the way that the late stage runtime optimization turns so much into constants, I believe that most things that in other shading languages would have been uniform variables are actually turned into explicit uniform constants already. And so the number of things that are not constant but still really need to be uniform, I bet are fairly small. Like the example of the loop control variable or that frequency scale, like that's the odd case it'll be. It's not going to be proliferating through the shader. Although we may want to take advantage of some more of those optimizations later, but I don't think that's going to kill us at first.
Yeah, if everything was varying, it wouldn't kill us unless it was a purely compute code. But it's worth it simply for these loops, because I've noticed these little loops from 0 to 3 are all over the place. And anytime there's an indirect lookup, knowing it's an actual uniform value being passed in, is a big deal to be able to optimize on that, especially if we're going to a library function. But
yeah, I think that's a super cool feature, because so say you're writing an ISPC, you have to explicitly say this is uniform, this is varying, but all that information is ultimately can be reduced, and you can kind of reduce it way better than a human can.
That's part of the nice thing about a language like this, where we've separated the expression language of the shaders from the underlying implementation. So we can do all those, analysis bits in between, because there's a translation step there. So hopefully we can shield shader writers from ever having to know details like that.
Just a quick comment, if I may. So for years, I think we've all been lamenting, OSL is wonderful, but why have these snippets around it, right? And nobody did anything about it, so I just want to thank you for what you guys for doing that. It's great.
You're welcome. Another question? Oh.
I have one more question. Were there any library functions where it was actually very difficult to create Cindy code for? Or was everything basically?
I think it's fair to say it's all still very much a work in progress.
Some are easier than others. So in this slide here, wherever I show the Perlin scalar, there could be another 10 slides on what I did inside of Perlin scalar, and even more on Gaber. Now, it's not too difficult for me because I do it all the time. But it could be. And so, like some of my notes here I said was, you want to look at the optimization report. When you slap on that Pragma SIMD, there's an optimization report you can also turn on, and it'll tell you whether it actually vectorized, and if not, tell you why. And so just by working through the whys it gives you, maybe it's a non-inline function, a very probable one is we could vectorize this, but we think it would be faster in scalar because it's a gather to a gather to a gather to a gather. And I don't know if you saw the previous presentation on the optimization of the denoise. That's a slide that Louis over here presented in the previous session. This is going to be online at some point in the future until probably until SIGGRAPH 217 would find it, hopefully. Yeah. Okay.
Maybe, Alex, maybe when that gets posted up online, you can put a link to the right place in the email site, just like send it to the OSL mail list.
Sure.
Because I don't be looking for this.
Yeah, that would be interesting to see what's going on there.
Yeah, well, where I was going with that is a lot of the optimizations we did for the denoise, I did the same things in this scalar here, you know, and a lot of that is let's hoist all the conditionals out we can, templatize it, call a correctly, tightly compiled version. So actually, if I look at the Gaber noise now, I think I compile like 12 plus different versions of it, depending on your filtering properties and other things. These are things in the original code that sort of got inside the inner loop and then did some ifs. You know, if the filtering is, you know, anesiotropic, you know, is the filtering enabled for this particular data lane and so on. These are things that we could hoist this out and check it on the outside, and it's going to be true for the whole batch. And there might even be some things that you could just, you know, even if it's something varying, you could see if it's, you could actually, well, yeah, it's varying, but is it really? Let me check all the data lanes. If they're all the same, let me call a specialized version of it. So some of those things, it would have vectorized not doing them, but I like to remove as many conditionals as possible. And for some of these, just looking, it did an amazing job with them in producing the code. So, more questions? Well, thanks for sticking around, everyone.